billions of years, our universe has been expanding, cooling and evolving into the cosmic home we know today. Stars have been born and died, galaxies have danced across the void, and somewhere in this vast expanse, life itself emerged. But how did it all begin? What sparked the very first moment of existence? The Big Bang Theory has been our best answer for nearly a century. It tells us that everything we see, from the smallest atom to the largest galaxy cluster, emerged from an incredibly hot, dense point, roughly 13.8 billion years ago. In less than a fraction of a second, space itself expanded faster than the speed of light, creating the stage upon which the cosmic drama would unfold. This theory has guided our understanding of the universe for generations. It explains why galaxies are moving away from us, why the night sky glows with ancient radiation, and how the first elements formed in the fiery moments after creation. Nobel Prizes have been awarded for discoveries that support this remarkable story. But what if we have been looking at this all wrong? What if the Big Bang Theory, as elegant and well supported as it appears, is missing crucial pieces of the puzzle? What if our understanding of the universe's birth is fundamentally incomplete? Recent discoveries in physics and astronomy have begun to challenge some of our most basic assumptions about cosmic origins. Dark matter and dark energy, two mysterious components that make up 95% of everything that exists, were completely unknown when the Big Bang Theory was first proposed. Quantum mechanics has revealed a universe far stranger than anyone imagined, where particles can exist in multiple states simultaneously, and reality itself seems to depend on observation. Advanced telescopes have peered deeper into space and further back in time than ever before, revealing structures and phenomena that don't quite fit our existing models. Computer simulations of the early universe sometimes produce results that contradict what we observe in the real cosmos. Meanwhile, theoretical physicists have proposed alternative scenarios that could explain our universe's existence without requiring a traditional beginning at all. Tonight, we embark on a journey to explore these mysteries. We will examine the evidence that supports the Big Bang Theory, but also investigate the growing list of problems that have emerged as our knowledge has expanded. We will consider radical alternatives, from cyclic universes that expand and contract forever, to quantum realities where multiple universes exist simultaneously. This is not about dismissing decades of careful scientific work. Instead, it is about embracing the spirit of inquiry that drives science forward. The greatest discoveries often come when we question our most cherished beliefs and remain open to revolutionary new ideas. We will explore how the universe might have emerged from quantum fluctuations rather than a singular explosion. We will consider whether time itself might be an illusion, making the question of a beginning meaningless. We will examine the possibility that our universe is just one of infinitely many, each with its own laws of physics and its own story. The journey ahead will take us to the very edges of human knowledge, where mathematics and philosophy meet, where the impossible becomes possible, and where the search for truth reveals just how much we still have to learn. Whether the Big Bang Theory survives this scrutiny or gives way to something entirely new, the quest to understand our cosmic origins continues to inspire wonder and drive discovery. So, let us begin this exploration with open minds and curious hearts. The universe has been keeping its secrets for nearly 14 billion years. Tonight, we attempt to unlock them. The story of the Big Bang Theory begins not with a cosmic explosion, but with a quiet observation in a California observatory in 1929. Edwin Hubble, peering through the 100-inch telescope at Mount Wilson, was about to change our understanding of the universe forever. For centuries, astronomers had assumed that the cosmos was static and eternal. Even Albert Einstein, when he developed his theory of general relativity in 1915, initially believed the universe was unchanging. He was so convinced of this that he added a mathematical term called the cosmological constant to his equations, specifically to prevent the universe from expanding or contracting. But Hubble's observations told a different story. As he studied distant galaxies, he noticed something peculiar about their light. The light from these galaxies appeared redder than it should be, as if it had been stretched during its journey through space. This phenomenon, called redshift, suggested that these galaxies were moving away from us at incredible speeds. Even more surprising was the pattern Hubble discovered. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, implied something extraordinary about the nature of space itself. If every distant galaxy was moving away from us, and the farther galaxies were moving faster, then the entire universe must be expanding. But Hubble was not the first to consider this possibility. A few years earlier, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre had proposed what he called the hypothesis of the primeval atom. Lemaitre suggested that if the universe was expanding now, it must have been smaller in the past. Extrapolating backward, he reasoned that everything in the universe must have once been compressed into an incredibly dense, hot state. Lemaitre imagined this primeval atom as containing all the matter and energy that would eventually become stars, planets, and galaxies. He proposed that this cosmic egg had somehow exploded or expanded, setting the universe on its current path of growth and cooling. It was a radical idea that challenged the prevailing view of an eternal, unchanging cosmos. Initially, many scientists were skeptical. The idea seemed to have religious overtones that made some uncomfortable. Others questioned whether the evidence was strong enough to support such a dramatic conclusion. The British astronomer Fred Hoyle was particularly critical, dismissing Lemaitre's idea as just another creation myth dressed up in scientific language. Ironically, it was Hoyle who gave the theory its popular name. During a BBC radio broadcast in 1949, he referred mockingly to Lemaitre's hypothesis as the Big Bang Theory. The name stuck, even though Hoyle intended it as criticism rather than endorsement. As more observations accumulated, however, the evidence for an expanding universe became undeniable. In 1948, the Russian-American physicist George Gamow and his colleagues Ralph Alpher and Robert Herman made a crucial prediction. They calculated that if the universe had indeed begun in a hot, dense state, it should have left behind a faint afterglow of radiation that would still be detectable today. This cosmic microwave background radiation, as it came to be known, would be the smoking gun that could prove the Big Bang Theory correct. The radiation should be visible in all directions of the sky, a remnant of the time when the universe first became transparent to light, roughly 380,000 years after the initial expansion began. For nearly 2 decades, this prediction remained untested. The technology to detect such faint radiation simply did not exist. But in 1965, 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon exactly what Gamow and his team had predicted. Penzias and Wilson were trying to eliminate noise from their radio antenna when they discovered a persistent signal coming from every direction in the sky. At first, they thought it might be interference from nearby New York City, or perhaps droppings from pigeons that had nested in their equipment. But after cleaning out the pigeons and checking every possible source of contamination, the signal remained. When they consulted with theoretical physicists, they learned that they had discovered the cosmic microwave background radiation. This ancient light, stretched and cooled by billions of years of cosmic expansion, provided compelling evidence that the universe had indeed begun in a hot, dense state. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their accidental but revolutionary discovery. The detection of the cosmic microwave background transformed the Big Bang from a speculative hypothesis into mainstream scientific theory. Here was direct evidence that the universe had a beginning, that it had evolved from a fundamentally different state than what we observe today. But even as the Big Bang theory gained acceptance, questions remained. What had caused the initial expansion? What had existed before the Big Bang? And why did the universe have the particular properties we observe today? These questions would drive cosmological research for decades to come, leading to new discoveries that would both support and challenge our understanding of cosmic origins. The idea of an expanding universe changed everything. But does it capture the whole story? By the 1970s, astronomers had assembled the cosmic microwave background radiation, galaxy redshift observations, and theoretical predictions into a comprehensive story of how our universe began and evolved. This became known as the Standard Model of Cosmology, and it remains the foundation of our understanding today. According to this model, everything we can observe in the universe emerged from an incredibly small, hot, and dense point roughly 13.8 billion years ago. This initial state was not an explosion in space, but rather an expansion of space itself. Imagine a balloon being inflated, but instead of air filling the balloon, space itself was growing and carrying matter along with it. The universe began in what physicists call a singularity, a point where the normal laws of physics break down completely. At this moment, all the matter and energy that would eventually become billions of galaxies was compressed into a region smaller than the period at the end of this sentence. The temperature was infinite, the density was infinite, and time itself may not have had any meaning. In the very first moments after this expansion began, the universe underwent a period of rapid inflation. During the first tiny fraction of a second, specifically between 10 to the negative 36 and 10 to the negative 32 seconds, space expanded faster than the speed of light. The universe grew from smaller than a proton to roughly the size of a grapefruit, in less time than it takes light to cross the nucleus of an atom. This inflationary period, proposed by physicist Alan Guth in 1980, helped explain why the universe appears so uniform in all directions despite its vast size. During inflation, tiny quantum fluctuations in the fabric of space itself were stretched to enormous scales. These microscopic variations in density would later become the seeds from which galaxies and galaxy clusters would grow. Without these primordial fluctuations, the universe would have remained perfectly smooth and featureless, never developing the rich structure we observe today. The earliest moments we can meaningfully discuss begin at what physicists call Planck time, about 10 to the negative 44 seconds after the initial expansion started. Before this moment, our current understanding of physics breaks down completely. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single superforce. The concepts of space and time as we know them may not have existed in any recognizable form. As the universe continued to expand and cool from its initial state of unimaginable heat, the fundamental forces began to separate from one another in a process physicists call symmetry breaking. First, gravity split off from the other forces when the universe was only 10 to the negative 36 seconds old and had a temperature of about 10 to the 28 degrees Celsius. This separation of gravity marked the end of what cosmologists call the Planck epoch and the beginning of the grand unification epoch. At 10 to the negative 34 seconds, when the temperature had dropped to 10 to the 27 degrees Celsius, the strong nuclear force separated from the electroweak force. This transition triggered the period of cosmic inflation, as the energy released by this symmetry breaking drove the exponential expansion of space itself. The universe was still unimaginably hot and dense, filled with exotic particles and antiparticles that have no counterpart in today's cooler cosmos. The inflationary period ended at about 10 to the negative 32 seconds, when the inflaton field that drove expansion finally decayed into ordinary matter and radiation. This process, called reheating, filled the universe with a hot soup of elementary particles including quarks, electrons, photons, and neutrinos. The temperature at this point was still about 10 to the 25 degrees Celsius, far too hot for any complex structures to form. By 10 to the negative 12 seconds, the temperature had dropped to about 10 to the 15 degrees Celsius, cool enough for the electroweak force to split into the electromagnetic force and the weak nuclear force that governs radioactive decay. At this point, all four fundamental forces had assumed their modern identities, and the basic rules that govern physics today were in place. As the universe continued to expand and cool, the exotic particles that filled the early cosmos began to annihilate with their antiparticle counterparts. For reasons that physicists still don't fully understand, there was a slight asymmetry between matter and antimatter. For every billion antiparticles, there were 1,000,000,001 particles of normal matter. When the annihilation process was complete, only this tiny excess of matter remained, and this leftover material would eventually form all the stars, planets, and galaxies we see today. By the time the universe was 1 microsecond old, it had cooled to about 10 trillion degrees Celsius. At this temperature, quarks and gluons could finally bind together to form protons and neutrons, the building blocks of atomic nuclei. This transition, called the quark confinement epoch, marked the first time that particles resembling those we know today could exist in the universe. When the universe reached 1 second of age, it had cooled to about 10 billion degrees Celsius. The density was still about 100,000 times greater than water, but conditions were finally mild enough for the first nuclear reactions to begin. Protons and neutrons started combining to form the nuclei of the lightest elements in a process called Big Bang nucleosynthesis. During the next 20 minutes, about 25% of all protons were converted into helium nuclei, while trace amounts of lithium, beryllium, and boron were also produced. The nuclear reaction stopped when the universe had expanded and cooled enough that the particles were no longer colliding with sufficient energy to fuse together. This cosmic furnace produced almost exactly the abundances of light elements that we observe in the universe today, providing one of the strongest pieces of evidence for the Big Bang model. For the next 380,000 years, the universe remained in a state that physicists call a plasma. Free electrons scattered photons in all directions, making space completely opaque to light. If you could have been present during this era, looking in any direction would have been like staring into the surface of the sun. The universe was filled with a glowing fog of ionized hydrogen and helium, with temperatures slowly dropping from thousands to hundreds of degrees Celsius. But as the universe continued to expand and cool, it eventually reached a temperature of about 3,000 degrees Celsius. At this critical point, electrons could finally combine with nuclei to form complete, neutral atoms, mostly hydrogen and helium. This process, called recombination, happened relatively quickly throughout the universe, clearing the cosmic fog and allowing light to travel freely through space for the first time. This moment marked a fundamental transition in cosmic history. The photons released during recombination have been traveling through space ever since, cooling and stretching as the universe expanded. Today, we detect these ancient photons as the cosmic microwave background radiation. Cooled by 13.8 billion years of cosmic expansion to just 2.7 degrees above absolute zero, the cosmic microwave background provides us with a baby picture of the universe, showing the state of matter when the cosmos was only 380,000 years old. Tiny variations in temperature across this ancient light correspond to slight density differences in the primordial gas. These small irregularities, originally created by quantum fluctuations during inflation, would grow over billions of years into the galaxies and galaxy clusters we observe today. After recombination, the universe entered what cosmologists poetically call the Dark Ages. There were no stars yet, no galaxies, and no sources of light except the fading glow of the cosmic microwave background. The universe was filled with vast clouds of hydrogen and helium gas, slowly growing denser in some regions due to the relentless pull of gravity, acting on the density variations left over from the early universe. Over tens of millions of years, these gas clouds continued to collapse under their own weight. The first regions to collapse were the densest, where dark matter had already begun to form gravitational wells that attracted normal matter. As the gas fell into these wells, it heated up due to gravitational compression. When the core temperature reached about 10 million degrees Celsius, nuclear fusion ignited, and the first stars were born. These early stars were very different from the Sun. They were much more massive, perhaps 50 to 100 times heavier, and they burned much hotter and brighter. Because they contained only hydrogen and helium with virtually no heavier elements, they were able to grow to enormous sizes before the pressure of their own radiation balanced the inward pull of gravity. These first-generation stars, called Population 3 stars, lived fast and died young. Their massive size meant they burned through their nuclear fuel in just a few million years, compared to the 10 billion year lifetime expected for a star like our Sun. When they exhausted their fuel, they exploded as supernovas, scattering the heavier elements they had created in their cores throughout the surrounding space. The explosions of these early supernovas enriched the universe with carbon, oxygen, silicon, iron, and dozens of other elements that had never existed before. These heavy elements mixed with the primordial hydrogen and helium, providing the raw materials for a new generation of stars, and eventually for rocky planets like Earth. We have built a model, a narrative, that connects the earliest moments of cosmic time to the present day. But is it complete, or have we misunderstood the details? Despite its remarkable success in explaining many features of our universe, the Big Bang Theory faces several profound challenges that have puzzled cosmologists for decades. These problems don't necessarily invalidate the theory, but they suggest that our understanding of cosmic origins may be incomplete or fundamentally flawed in ways we are only beginning to appreciate. The first major problem is known as the horizon problem, and it strikes at the heart of one of the Big Bang Theory's greatest successes. When we observe the cosmic microwave background radiation, we find that it has almost exactly the same temperature in all directions across the sky. The temperature varies by only about 1 part in 100,000, making it one of the most uniform things ever measured in nature. This uniformity seems natural until you consider the vast distances involved. The cosmic microwave background comes from regions of space that are now separated by billions of light years. In the standard Big Bang model, these regions were never in contact with each other. They were beyond each other's horizons, meaning that light signals could never have traveled between them in the time available since the Big Bang began. Think of it this way: if you shine a flashlight in one direction and your friend shines a flashlight in the opposite direction, those beams of light represent the farthest distance that information could have traveled in the time since the universe began. In the Big Bang model, regions of space that are now separated by more than twice this distance should never have been able to communicate with each other. Yet, when we look at the cosmic microwave background radiation coming from these supposedly disconnected regions, we find they all have the same temperature, to within a few thousandths of a degree. It's like finding that two isolated rooms in different buildings, with no connection between them, have maintained identical temperatures for billions of years. In physics, isolated systems typically reach thermal equilibrium only when they can exchange energy and information. Without such contact, we would expect these distant regions to have very different temperatures. The mathematical problem is stark. In the standard Big Bang model, the observable universe today originated from about 100,000 separate regions that were never in causal contact with each other during the early universe. Each of these regions should have had its own random temperature, yet somehow they all ended up at virtually the same value. The probability of this happening by chance is astronomically small, far less likely than winning the lottery every day for millions of years. The horizon problem suggests that either our understanding of the early universe is wrong, or some mechanism allowed widely separated regions to communicate and equilibrate before the cosmic microwave background was created. The inflationary model proposed by Alan Guth was specifically designed to solve this problem by suggesting that all observable regions of the universe were once in close contact before being rapidly stretched apart during inflation. But inflation itself creates new puzzles. The mechanism that supposedly drove inflation, called the inflaton field, has never been directly observed or satisfactorily explained. We don't know what this field was made of, why it started inflating, or why it stopped. The mathematical models of inflation require very specific and seemingly arbitrary initial conditions to work properly. The inflaton field must have started with just the right energy density and just the right rate of decay to produce the universe we observe. Critics argue that inflation doesn't really solve the horizon problem, but simply pushes it back to an earlier time, when we understand even less about physics. Instead of asking why distant regions of the cosmic microwave background have the same temperature, we now have to ask why the inflaton field had the same properties everywhere. We've replaced one fine-tuning problem with another that may be even more severe. Furthermore, some versions of inflation predict that the process should never stop completely. In these eternal inflation models, different regions of space continue inflating at different rates, creating an infinite number of separate universes with different physical properties. This multiverse scenario is virtually impossible to test experimentally, leading some physicists to question whether inflation can be considered a scientific theory at all. The second major challenge is called the flatness problem. When cosmologists measure the geometry of space, they find that our universe appears to be remarkably flat. In Einstein's theory of general relativity, the curvature of space depends on the total density of matter and energy it contains. If the density is too high, space curves back on itself like the surface of a sphere. If it's too low, space curves outward like a saddle. The critical density that produces flat space is about 6 hydrogen atoms per cubic meter. When astronomers add up all the matter and energy they can observe, including the mysterious dark matter and dark energy, they find that the total density is within 1% of this critical value. This seems like a remarkable coincidence. In the early universe, the situation would have been even more delicate. The density parameter, which measures how close the actual density is to the critical value, evolves over time. In a universe that starts with a density slightly higher than critical, this parameter grows rapidly as the universe evolves. In a universe that starts with a density slightly lower than critical, the parameter shrinks towards zero. The mathematics show that if the density in the early universe had been even slightly higher than the critical value, the universe would have collapsed back on itself within thousands of years. If it had been slightly lower, the universe would have expanded so rapidly that matter could never have clumped together to form stars and galaxies. The fact that we exist at all suggests that the initial density was fine-tuned to extraordinary precision. Some calculations suggest that the density in the early universe had to be accurate to within 1 part in 10 to the 60th power to produce the flat universe we observe today. To put this number in perspective, 10 to the 60th is larger than the number of atoms in the observable universe. This level of precision is almost incomprehensible. It would be like balancing a pencil on its point for billions of years without it falling over, or like throwing a dart at a target the size of a proton from a distance of several light years and hitting the bullseye perfectly. Such fine-tuning seems to require either incredible luck or some underlying mechanism that we don't yet understand. The anthropic principle suggests that we observe these seemingly special conditions simply because we exist to observe them. In other words, if the universe had different properties, we wouldn't be here to wonder about them. But many physicists find this explanation unsatisfying, because it doesn't really explain why the universe has the properties it does. The third problem involves the mysterious components that seem to dominate our universe. When astronomers try to account for all the matter and energy in the cosmos, they find that ordinary matter, the stuff that makes up stars, planets, and people, accounts for less than 5% of the total. The remaining 95% consists of dark matter and dark energy, two components that interact with ordinary matter and light so weakly that we can detect them only through their gravitational effects. Dark matter was first proposed in the 1930s when the Swiss astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving faster than expected based on the amount of visible matter they contained. The galaxies should have been moving slowly enough to remain gravitationally bound to the cluster, but they appeared to be moving so fast that they should have escaped long ago. Zwicky calculated that the cluster must contain about 10 times more matter than could be seen in the form of stars and gas. He called this invisible component dark matter. Though at the time, most astronomers dismissed his conclusion as the result of observational errors or incomplete understanding of galaxy dynamics, the evidence for dark matter became overwhelming in the 1970s when Vera Rubin and Kent Ford studied the rotation curves of spiral galaxies. They found that the outer regions of galaxies were rotating faster than expected based on the amount of visible matter they contained. According to Newton's laws of gravity, the outer regions should be moving more slowly than the inner regions, just as the outer planets in our solar system orbit more slowly than the inner ones. Instead, Rubin and Ford found that most galaxies rotate like rigid disks, with their outer edges moving just as fast as their centers. The only way to explain this observation was to assume that galaxies contain about 5 times more matter than we can see. This invisible matter must be distributed in a roughly spherical halo around each galaxy, providing the extra gravitational pull needed to keep the outer stars moving at their observed speeds. Since then, evidence for dark matter has accumulated from many different sources. Gravitational lensing observations show that massive galaxy clusters bend light in ways that require much more matter than can be seen. Computer simulations of cosmic structure formation can reproduce the observed distribution of galaxies only if they include large amounts of dark matter. The cosmic microwave background radiation shows acoustic oscillations that depend on the ratio of dark matter to ordinary matter. Despite decades of increasingly sophisticated searches, physicists have failed to directly detect dark matter particles. Underground detectors, shielded from cosmic rays, have found no convincing evidence for dark matter interactions. particle accelerators have failed to produce any of the exotic particles that theorists have proposed as dark matter candidates. Satellite-based gamma-ray telescopes have not detected the radiation that should be produced when dark matter particles annihilate with each other. We know dark matter must be there because of its gravitational effects, but it seems to interact with ordinary matter only through gravity. This makes dark matter unlike any known form of matter. Some physicists have proposed exotic new particles like weakly interacting massive particles or axions to explain dark matter. Others have suggested that our understanding of gravity itself might be wrong, and that modified theories of gravity could eliminate the need for dark matter entirely. Even more mysterious is dark energy, the component that appears to make up about 70% of the universe. Dark energy was discovered in 1998, when two teams of astronomers studying distant supernovas found that the expansion of the universe is actually accelerating. This was completely unexpected because gravity should be slowing down the expansion over time. The Type 1a supernovas that these teams studied are remarkably uniform in their brightness, making them excellent standard candles for measuring cosmic distances. By comparing the apparent brightness of distant supernovas with their known intrinsic luminosity, astronomers can determine how far away they are. By measuring the redshift of their light, they can determine how fast they were receding when the light was emitted. What the teams found was shocking. The most distant supernovas appeared fainter than expected, indicating that they were farther away than predicted by models of a decelerating universe. The only way to explain this observation was to conclude that the expansion of the universe had been speeding up since the light left those distant galaxies. The only way to explain accelerating expansion is to assume that empty space itself contains energy that acts like a repulsive force. This dark energy pushes space apart, overwhelming the attractive force of gravity on large scales. Einstein's equations allow for such a component, which he originally introduced as the cosmological constant, to prevent his static universe model from collapsing. But when physicists try to calculate how much energy empty space should contain based on quantum mechanics, they get an answer that is catastrophically wrong. Quantum field theory predicts that the vacuum should be filled with virtual particles that constantly appear and disappear. The energy of these quantum fluctuations should contribute to the cosmological constant, but the calculated value is larger than the observed value by a factor of 10 to the 120th power. This discrepancy has been called the worst prediction in the history of physics. The theoretical value is so large that it would cause the universe to expand at an incredible rate, doubling in size every tiny fraction of a second. Obviously, this is not what we observe. Something must be cancelling out most of the vacuum energy, but physicists have no idea what that mechanism might be. The existence of dark matter and dark energy wasn't predicted by the original Big Bang theory. These components were discovered through observations and then added to the theory to make it consistent with what we see. This approach is scientifically valid, but it raises questions about whether we truly understand the fundamental nature of our universe, or whether we're simply patching holes in an incomplete theory. Another significant problem is the absence of magnetic monopoles. Many theories of particle physics predict that the extremely high energies present in the early universe should have created exotic particles called magnetic monopoles. Unlike ordinary magnets, which always have both north and south poles, magnetic monopoles would be particles with only a single magnetic pole. Grand unified theories, which attempt to unify the electromagnetic weak and strong nuclear forces, generically predict that magnetic monopoles should have been produced during phase transitions in the early universe. These theories suggest that monopoles should be incredibly massive, perhaps 10 to the 16th times heavier than a proton. But they should also be absolutely stable and immune to decay. If the Big Bang theory is correct, the universe should be flooded with these particles today. They should be as common as protons, or at least common enough to be easily detectable in cosmic ray experiments or particle accelerator searches. Yet despite extensive searches spanning several decades, no magnetic monopole has ever been found convincingly. The absence of magnetic monopoles creates what physicists call the monopole problem. Either the grand unified theories are wrong, or some mechanism eliminated the monopoles that should have been produced in the early universe. The inflationary model was partly developed to explain this absence, suggesting that inflation diluted the density of magnetic monopoles to undetectable levels by expanding space so rapidly that the few monopoles that were created became spread over enormous volumes. But this solution requires very specific assumptions about the timing and duration of inflation. The inflation must have started after the monopoles were created, but before they could multiply through interactions with other particles. The duration of inflation must have been long enough to dilute the monopole density, but not so long as to create other problems. These requirements place tight constraints on inflationary models and reduce their predictive power. The Big Bang Theory also struggles to explain the formation of the largest structures in the universe. Computer simulations based on the Standard Model can reproduce the overall pattern of galaxy distribution, but they have difficulty explaining some specific observations. For example, astronomers have discovered structures like the Great Wall, a chain of galaxies stretching across hundreds of millions of light-years, and the even larger Sloan Great Wall, which extends over more than 1 billion light-years. According to the Big Bang timeline, there may not have been enough time for gravity to assemble such enormous structures. The slight density variations in the cosmic microwave background, which serve as the seeds for all later structure formation, seem too small to have grown into these massive formations in only 13.8 billion years. Computer simulations show that structures this large should take much longer to form through gravitational collapse. This timing problem suggests that either our understanding of structure formation is incomplete or the universe is older than we think. Some astronomers have proposed that these large structures formed through non-gravitational processes, such as cosmic defects or phase transitions in the early universe. Others suggest that dark matter interacts with itself in ways that speed up structure formation, but none of these solutions has gained widespread acceptance. The theory also faces what cosmologists call the lithium problem. Big Bang nucleosynthesis makes specific predictions about how much lithium should have been created in the first few minutes after the expansion began. The nuclear reaction rates are well understood from laboratory experiments, and the density of ordinary matter has been precisely measured from observations of the cosmic microwave background. When astronomers measure the amount of lithium in old stars, which should preserve the primordial abundance from the Big Bang, they find only about 1/3 as much as the theory predicts. This discrepancy has persisted despite decades of attempts to resolve it through more careful observations and improved theoretical calculations. Some astronomers have suggested that the missing lithium was destroyed by unknown processes in stellar interiors. Convection currents might have carried lithium from the surface into the hot core, where it was burned in nuclear reaction. Others propose that our understanding of nuclear physics in the extreme conditions of the early universe might be flawed. The reaction rates might be different at the incredible temperatures and densities present during Big Bang nucleosynthesis. Still others wonder whether this discrepancy points to more fundamental problems with the Big Bang scenario. Perhaps the universe went through additional phases that destroyed lithium after nucleosynthesis was complete. Or perhaps the assumptions about the uniformity and isotropy of the early universe are incorrect, leading to spatial variations in element production. Perhaps most troubling of all is the singularity problem. The Big Bang theory traces the history of the universe back to a point where all matter and energy were compressed into a region of zero size and infinite density. At this singularity, the laws of physics as we know them break down completely. Temperature, pressure, and density all become infinite, while time itself may cease to have meaning. Most physicists believe that singularities represent the limits of our current theories, rather than physical reality. When a theory predicts infinite quantities, it usually means the theory is being pushed beyond its range of validity. General relativity is a classical theory that doesn't account for quantum effects. And these effects become important when matter is compressed to incredibly high densities. But if the Big Bang theory breaks down at the most crucial moment in cosmic history, how can we trust its predictions about what happened afterward? The singularity problem suggests that we need a quantum theory of gravity to understand the universe's origins. Such a theory would merge general relativity with quantum mechanics, potentially eliminating the singularity and providing a more complete picture of cosmic birth. Several approaches to quantum gravity have been proposed, including string theory, loop quantum gravity, and causal dynamical triangulation. But none has yet achieved the level of development and experimental support enjoyed by the standard Big Bang model. Until we have a working theory of quantum gravity, the the ultimate origin of the universe remains shrouded in mystery. These problems don't necessarily mean that the Big Bang Theory is wrong. Science progresses by identifying the limitations of existing theories and developing new ones that can address previously unexplained phenomena. The Big Bang Theory successfully explains many observations and continues to make testable predictions, but the accumulating list of problems suggests that our current understanding of cosmic origins is far from complete. Even the most celebrated theories can reveal cracks when we look closely enough. As the problems with the Big Bang Theory have accumulated, physicists and cosmologists have proposed various alternative models to explain the origin and evolution of our universe. These alternatives range from minor modifications to the standard model to radical departures that challenge our most basic assumptions about time, space, and cosmic history. The first major alternative to emerge was the steady-state theory, proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle. This elegant model suggested that the universe had no beginning and would have no end. Instead of starting with a Big Bang, the universe had always existed in roughly the same state, continuously creating new matter to maintain constant density as space expanded. The steady-state theory was based on what its creators called the perfect cosmological principle. While the Big Bang model assumed that the universe was homogeneous in space but changed over time, the steady-state model proposed that the universe was homogeneous in both space and time. No matter when or where you observed the cosmos, it would always look essentially the same. To maintain this eternal uniformity, the theory required that new matter be continuously created throughout space. As the universe expanded and existing matter became more diluted, new hydrogen atoms would spontaneously appear in the empty regions between galaxies. The rate of matter creation needed to be very small, only about 1 hydrogen atom per cubic meter every few billion years. Far too little to be directly observable. This continuous creation might seem to violate the conservation of energy, one of the most fundamental principles in physics. But Hoyle and his colleagues argued that the expanding universe itself provided a reservoir of negative energy that could balance the positive energy of newly created matter. In their view, the total energy of the universe remained zero throughout its eternal history. The steady-state theory had several appealing features. It eliminated the need for a singular beginning, avoiding the uncomfortable questions about what came before the Big Bang and what caused it to happen. It also made specific predictions that could be tested through observations. If the universe had always looked the same, then distant galaxies observed at earlier times should have the same properties as nearby galaxies observed today. For more than a decade, the steady-state and Big Bang theories competed on roughly equal footing. Both could explain the observed expansion of the universe and the abundances of hydrogen and helium. The steady-state theory actually had an advantage in explaining why the universe appeared so uniform, since it had infinite time to reach equilibrium, rather than the limited time available in the Big Bang model. However, the discovery of the cosmic microwave background radiation in 1965 dealt a severe blow to the steady-state theory. This ancient radiation represented a clear sign that the universe had been much hotter and denser in the past, contradicting the steady-state assumption that conditions had always been the same. The temperature and properties of the cosmic microwave background matched the predictions of Big Bang nucleosynthesis almost perfectly. Further observations in the following decades continued to favor the Big Bang model. Radio astronomers discovered that distant galaxies had different properties than nearby ones, showing that the universe had indeed evolved over time. The abundances of light elements in old stars matched Big Bang predictions better than steady-state alternatives. By the 1980s, most cosmologists had abandoned the steady-state theory in favor of the Big Bang model. But Fred Hoyle never gave up on his vision of an eternal universe. In the 1990s, he collaborated with Jeffrey Burbidge and Jayant Narlikar to propose a quasi-steady-state cosmology that attempted to reconcile continuous creation with the observed cosmic microwave background. This modified theory suggested that the universe underwent periodic oscillations with brief periods of rapid expansion, followed by longer periods of steady-state evolution. During the expansion phases, the universe would heat up and create the kind of radiation we observe as the cosmic microwave background. During the steady-state phases, continuous matter creation would proceed, as in the original theory. This quasi-steady-state model could potentially explain both the observed radiation and the long-term uniformity of the universe, but it required many additional assumptions and never gained widespread acceptance. Today, most physicists regard the steady-state theory as a historical curiosity, an elegant idea that was ultimately contradicted by observations. But some of its insights have influenced modern alternatives to the Big Bang, particularly the idea that the universe might have no beginning or end. The steady-state theory also demonstrated that seemingly obvious assumptions about cosmic history, such as the idea that the universe must have had a beginning, could be challenged by careful theoretical work. A more promising alternative that has gained significant attention in recent years is the cyclic universe model, also known as the Big Bounce theory. This approach suggests that our universe is just the latest in an infinite series of expansions and contractions. Instead of beginning with a Big Bang, our current expansion phase emerged from the collapse and subsequent rebound of a previous universe. The basic idea of a cyclic universe is ancient, appearing in Hindu and Buddhist cosmologies thousands of years ago. But the modern scientific version was developed in the early 2000s by Paul Steinhardt, Neil Turok, and their collaborators. Their model attempts to solve many of the problems that plague the standard Big Bang theory while maintaining consistency with observed phenomena. In the cyclic model, the universe alternates between periods of expansion and contraction on a timescale of trillions of years. During the expansion phase, which we are currently experiencing, galaxies move apart and the universe cools, much as in the standard Big Bang model. But instead of expanding forever, the expansion eventually slows down and reverses due to the effects of dark energy, which changes its properties over time. During the contraction phase, galaxies approach each other and the universe heats up as it becomes smaller and denser. But instead of collapsing to a singularity, as in the Big Bang model, quantum effects become important when the universe reaches extremely high densities. These quantum effects cause the universe to bounce back into a new expansion phase, beginning the cycle anew. The cyclic model elegantly solves several problems that plague the Big Bang theory. The flatness problem disappears because the universe has infinite time to approach the critical density through natural evolution. The horizon problem is resolved because distant regions had time to communicate during previous cycles. The model also eliminates the need for cosmic inflation, which many physicists find unsatisfying due to its arbitrary initial conditions. According to the cyclic theory, the cosmic microwave background radiation we observe today was not created during the Big Bang, but during the most recent bounce from the previous contraction phase. The nearly uniform temperature of this radiation reflects the fact that the entire universe was in thermal equilibrium just before the bounce occurred. The model makes specific predictions that differ from standard Big Bang cosmology. For example, it predicts that primordial gravitational waves, ripples in space-time itself that should have been created during inflation, will have a different spectrum than predicted by inflationary models. Future gravitational wave detectors may be able to distinguish between these predictions and determine which model is correct. However, the cyclic model faces significant challenges of its own. The bouncing mechanism requires exotic forms of matter or energy that have never been observed directly. The equations describing the bounce are extremely complex and may not have stable solutions. Some versions of the model predict that entropy increases with each cycle, eventually leading to a heat death scenario that contradicts the assumption of eternal cycling. Another fascinating alternative is based on loop quantum gravity, one of the leading candidates for a theory of quantum gravity. In this approach, space and time themselves are made of discrete, indivisible units at the smallest scales, much like matter is made of atoms. This granular structure of space-time prevents the formation of singularities and provides a natural mechanism for cosmic bounces. Loop quantum cosmology, the application of loop quantum gravity to the entire universe, suggests that our Big Bang was actually a big bounce from a previous contracting phase. As the universe contracted in the distant past, it approached but never reached infinite density. Instead, quantum effects caused space and time to rebound when the universe reached the maximum possible density allowed by the discrete structure of space-time. This quantum bounce naturally explains the initial conditions that seem so carefully fine-tuned in the standard Big Bang model. The uniformity and flatness we observe today are natural consequences of the smooth approach to maximum density during the previous contraction. The tiny density variations that seeded galaxy formation were created by quantum fluctuations during the bounce itself. Loop quantum cosmology makes testable predictions about the cosmic microwave background that differ subtly from both standard Big Bang and inflationary models. The theory predicts specific patterns of temperature variations that future observations may be able to detect. It also suggests that signatures of the previous universe before the bounce might be encoded in the cosmic microwave background, providing a window into pre-Big Bang physics. Yet another alternative comes from string theory, the attempt to unify all fundamental forces by describing particles as tiny, vibrating strings, rather than point-like objects. String cosmology suggests that our universe might be one of many branes, multi-dimensional surfaces floating in a higher dimensional space called the bulk. In some string theory models, our Big Bang was triggered by the collision of two branes in the bulk. These brane collisions could occur repeatedly, creating multiple universes or multiple Big Bang events within the same universe. The extra dimensions predicted by string theory provide new possibilities for matter and energy that don't exist in our familiar three-dimensional space. The ekpyrotic scenario, developed by Justin Corey, Bert Overott, Paul Steinhardt, and Neil Turok, is one specific string theory-inspired model. In this scenario, our universe exists on a brane that periodically collides with a parallel brane. These collisions create the hot, dense conditions we associate with the Big Bang, but the underlying branes continue to exist and can collide again in the future. String cosmology also suggests the possibility of a pre-Big Bang phase in which the universe existed in a fundamentally different state. In these models, time might extend infinitely into the past, eliminating the need for a temporal beginning altogether. The apparent Big Bang would be just a transition from one phase of cosmic evolution to another, rather than the ultimate origin of everything. However, string theory faces the challenge that it makes few testable predictions about observable phenomena. The extra dimensions are typically assumed to be compactified to incredibly small sizes, making them impossible to detect directly. The theory also allows for an enormous number of possible vacuum states, each corresponding to a different set of physical laws, making it difficult to predict what we should observe in our particular universe. More radical alternatives question whether the universe needs to have had a beginning at all. Some physicists have proposed models of eternal inflation, in which our observable universe is just one bubble in an infinite multiverse that has always existed. In these models, Big Bang-like events occur continuously throughout the multiverse, creating new bubble universes with different physical properties. The multiverse concept arises naturally from many inflationary models. If inflation occurred in our early universe, it probably occurred elsewhere as well. Different regions of space could undergo inflation at different times and for different durations, creating a fractal-like structure of bubble universes within an eternally inflating background. Each bubble universe would have its own Big Bang moment when inflation ended in that region, but the multiverse as a whole would have no beginning or end. Our observable universe represents just one small bubble in this vast cosmic foam, with physical constants and laws that may be completely different from those in other bubbles. The anthropic principle becomes important in multiverse scenarios. If different bubble universes have different physical laws, then only some will be capable of supporting the formation of stars, planets, and life. We necessarily find ourselves in a bubble universe with the right properties for our existence, regardless of how rare such properties might be in the multiverse as a whole. But the multiverse concept raises profound questions about the nature of scientific explanation. If anything that can happen does happen somewhere in the multiverse, then the specific properties of our universe become accidents of our location, rather than fundamental features that require explanation. Some philosophers and physicists argue that multiverse theories are unscientific because they make no testable predictions about what we should observe. Quantum mechanics itself suggests another alternative to the traditional Big Bang picture. In quantum cosmology, the universe doesn't begin with classical initial conditions, but emerges from a quantum state that exists outside of space and time. The wave function of the universe, proposed by Stephen Hawking and James Hartle, describes all possible cosmic histories simultaneously. In this view, asking what came before the Big Bang is like asking what lies north of the North Pole. Time itself emerges along with space during the quantum tunneling event that creates the universe. The apparent beginning of time in the Big Bang is not a moment when something started from nothing, but rather the boundary of space-time itself. The Hartley-Hawking no-boundary proposal suggests that the universe has no edge or boundary in time, but time, nevertheless, has a finite extent into the past. This is possible because time becomes space-like near the Big Bang, creating a geometry similar to the surface of a sphere. Just as the surface of the Earth has no edge, but still has finite area, the universe could have no temporal boundary, but still have finite age. Quantum cosmology makes specific predictions about the initial conditions of the universe that differ from classical Big Bang models. The theory suggests that the universe should emerge in its most probable quantum state, which turns out to be nearly flat and uniform. This could explain the apparent fine-tuning of initial conditions without requiring cosmic inflation or multiple universes. What if there was no singular beginning? What if the universe simply is, forever unfolding? As the problems with the Big Bang theory have accumulated, physicists and cosmologists have proposed various alternative models to explain the origin and evolution of our universe. These alternatives range from minor modifications to the standard model, to radical departures that challenge our most basic assumptions about time, space, and cosmic history. The first major alternative to emerge was the steady-state theory, proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle. This elegant model suggested that the universe had no beginning and would have no end. Instead of starting with a Big Bang, the universe had always existed in roughly the same state, continuously creating new matter to maintain constant density as space expanded. The steady-state theory was based on what its creators called the perfect cosmological principle. While the Big Bang model assumed that the universe was homogeneous in space but changed over time, the steady-state model proposed that the universe was homogeneous in both space and time. No matter when or where you observe the cosmos, it would always look essentially the same. To maintain this eternal uniformity, the theory required that new matter be continuously created throughout space. As the universe expanded and existing matter became more diluted, new hydrogen atoms would spontaneously appear in the empty regions between galaxies. The rate of matter creation needed to be very small, only about 1 hydrogen atom per cubic meter every few billion years, far too little to be directly observable. This continuous creation might seem to violate the conservation of energy, one of the most fundamental principles in physics. But Hoyle and his colleagues argued that the expanding universe itself provided a reservoir of negative energy that could balance the positive energy of newly created matter. In their view, the total energy of the universe remained zero throughout its eternal history. The steady-state theory had several appealing features. It eliminated the need for a singular beginning, avoiding the uncomfortable questions about what came before the Big Bang and what caused it to happen. It also made specific predictions that could be tested through observations. If the universe had always looked the same, then distant galaxies observed at earlier times should have the same properties as nearby galaxies observed today. For more than a decade, the steady-state and Big Bang theories competed on roughly equal footing. Both could explain the observed expansion of the universe and the abundances of hydrogen and helium. The steady-state theory actually had an advantage in explaining why the universe appeared so uniform, since it had infinite time to reach equilibrium, rather than the limited time available in the Big Bang model. However, the discovery of the cosmic microwave background radiation in 1965 dealt a severe blow to the steady-state theory. This ancient radiation represented a clear sign that the universe had been much hotter and denser in the past, contradicting the steady-state assumption that conditions had always been the same. The temperature and properties of the cosmic microwave background matched the predictions of Big Bang nucleosynthesis almost perfectly. Further observations in the following decades continued to favor the Big Bang model. Radio astronomers discovered that distant galaxies had different properties than nearby ones, showing that the universe had indeed evolved over time. The abundances of light elements in old stars matched Big Bang predictions better than steady-state alternatives. By the 1980s, Most cosmologists had abandoned the steady-state theory in favor of the Big Bang model, but Fred Hoyle never gave up on his vision of an eternal universe. In the 1990s, he collaborated with Geoffrey Burbidge and Jayant Narlikar to propose a quasi-steady-state cosmology that attempted to reconcile continuous creation with the observed cosmic microwave background. This modified theory suggested that the universe underwent periodic oscillations, with brief periods of rapid expansion followed by longer periods of steady-state evolution. During the expansion phases, the universe would heat up and create the kind of radiation we observe as the cosmic microwave background. During the steady-state phases, continuous matter creation would proceed as in the original theory. This quasi-steady-state model could potentially explain both the observed radiation and the long-term uniformity of the universe, but it required many additional assumptions and never gained widespread acceptance. Today, most physicists regard the steady-state theory as a historical curiosity, an elegant idea that was ultimately contradicted by observations. But some of its insights have influenced modern alternatives to the Big Bang, particularly the idea that the universe might have no beginning or end. The steady-state theory also demonstrated that seemingly obvious assumptions about cosmic history, such as the idea that the universe must have had a beginning, could be challenged by careful theoretical work. A more promising alternative that has gained significant attention in recent years is the cyclic universe model, also known as the Big Bounce theory. This approach suggests that our universe is just the latest in an infinite series of expansions and contractions. A change may be termed a cyclic universe. Instead of beginning with a Big Bang, our current expansion phase emerged from the collapse and subsequent rebound of a previous universe. The basic idea of a cyclic universe is ancient, appearing in Hindu and Buddhist cosmologies thousands of years ago. But the modern scientific version was developed in the early 2000s by Paul Steinhardt, Neil Turok, and their collaborators. Their model attempts to solve many of the problems that plague the standard Big Bang theory, while maintaining consistency with observed phenomena. In the cyclic model, the universe alternates between periods of expansion and contraction on a timescale of trillions of years. During the expansion phase, which we are currently experiencing, galaxies move apart and the universe cools, much as in the standard Big Bang model. But instead of expanding forever, the expansion eventually slows down and reverses due to the effects of dark energy, which changes its properties over time. During the contraction phase, galaxies approach each other and the universe heats up as it becomes smaller and denser. But instead of collapsing to a singularity as in the Big Bang model, quantum effects become important when the universe reaches extremely high densities. These quantum effects cause the universe to bounce back into a new expansion phase, beginning the cycle anew. The cyclic model elegantly solves several problems that plague the Big Bang theory. The flatness problem disappears because the universe has infinite time to approach the critical density through natural evolution. The horizon problem is resolved because distant regions had time to communicate during previous cycles. The model also eliminates the need for cosmic inflation, which many physicists find unsatisfying due to its arbitrary initial conditions. According to the cyclic theory, the cosmic microwave background radiation we observe today was not created during the Big Bang, but during the most recent bounce from the previous contraction phase. The nearly uniform temperature of this radiation reflects the fact that the entire universe was in thermal equilibrium just before the bounce occurred. The model makes specific predictions that differ from standard Big Bang cosmology. For example, it predicts that primordial gravitational waves, ripples in space-time itself that should have been created during inflation, will have a different spectrum than predicted by inflationary models. Future gravitational wave detectors may be able to distinguish between these predictions and determine which model is correct. However, the cyclic model faces significant challenges of its own. The bouncing mechanism requires exotic forms of matter or energy that have never been observed directly. The equations describing the bounce are extremely complex and may not have stable solutions. Some versions of the model predict that entropy increases with each cycle, eventually leading to a heat death scenario that contradicts the assumption of eternal cycling. Another fascinating alternative is based on loop quantum gravity, one of the leading candidates for a theory of quantum gravity. In this approach, space and time themselves are made of discrete, indivisible units at the smallest scales. much like matter is made of atoms. This granular structure of space-time prevents the formation of singularities and provides a natural mechanism for cosmic bounces. Loop quantum cosmology, the application of loop quantum gravity to the entire universe, suggests that our Big Bang was actually a big bounce from a previous contracting phase. As the universe contracted in the distant past, it approached but never reached infinite density. Instead, quantum effects caused space and time to rebound when the universe reached the maximum possible density allowed by the discrete structure of space-time. This quantum bounce naturally explains the initial conditions that seem so carefully fine-tuned in the standard Big Bang model. The uniformity and flatness we observe today are natural consequences of the smooth approach to maximum density during the previous contraction. The tiny density variations that seeded galaxy formation were created by quantum fluctuations during the bounce itself. Loop quantum cosmology makes testable predictions about the cosmic microwave background that differ subtly from both standard Big Bang and inflationary models. The theory predicts specific patterns of temperature variations that future observations may be able to detect. It also suggests that signatures of the previous universe before the bounce might be encoded in the cosmic microwave background, providing a window into pre-Big Bang physics. Yet another alternative comes from string theory, the attempt to unify all fundamental forces by describing particles as tiny vibrating strings, rather than point-like objects. String cosmology suggests that our universe might be one of many branes, multi-dimensional surfaces floating in a higher dimensional space called the bulk. In some string theory models, our Big Bang was triggered by the collision of two branes in the bulk. These brane collisions could occur repeatedly, creating multiple universes, or multiple Big Bang events, within the same universe. The extra dimensions predicted by string theory provide new possibilities for matter and energy that don't exist in our familiar three-dimensional space. The ekpyrotic scenario, developed by Justin Corey, Bert Overoot, Paul Steinhardt, and Neil Turok, is one specific string theory-inspired model. In this scenario, our universe exists on a brane that periodically collides with a parallel brane. These collisions create the hot, dense conditions we associate with the Big Bang, but the underlying branes continue to exist and can collide again in the future. The string cosmology also suggests the possibility of a pre-Big Bang phase, in which the universe existed in a fundamentally different state. In these models, time might extend infinitely into the past, eliminating the need for a temporal beginning altogether. The apparent Big Bang would be just a transition from one phase of cosmic evolution to another, rather than the ultimate origin of everything. However, string theory faces the challenge that it makes few testable predictions about observable phenomena. The extra dimensions are typically assumed to be compactified to incredibly small sizes, making them impossible to detect directly. The theory also allows for an enormous number of possible vacuum states, each corresponding to a different set of physical laws, making it difficult to predict what we should observe in our particular universe. More radical alternatives question whether the universe needs to have had a beginning at all. Some physicists have proposed models of eternal inflation in which our observable universe is just one bubble in an infinite multiverse that has always existed. In these models, Big Bang-like events occur continuously throughout the multiverse, creating new bubble universes with different physical properties. The multiverse concept arises naturally from many inflationary models. If inflation occurred in our early universe, it probably occurred elsewhere as well. Different regions of space could undergo inflation at different times and for different durations, creating a fractal-like structure of bubble universes within an eternally inflating background. Each bubble universe would have its own Big Bang moment when inflation ended in that region, but the multiverse as a whole would have no beginning or end. Our observable universe represents just one small bubble in this vast cosmic foam, with physical constants and laws that may be completely different from those in other bubbles. The anthropic principle becomes important in multiverse scenarios. If different bubble universes have different physical laws, then only some will be capable of supporting the formation of stars, planets, and life. We necessarily find ourselves in a bubble universe with the right properties for our existence, regardless of how rare such properties might be in the multiverse as a whole. But the multiverse concept raises profound questions about the nature of scientific explanation. If anything that can happen does happen somewhere in the multiverse, then the specific properties of our universe become accidents of our location, rather than fundamental features that require explanation. Some philosophers and physicists argue that multiverse theories are unscientific because they make no testable predictions about what we should observe. Quantum mechanics itself suggests another alternative to the traditional Big Bang picture. In quantum cosmology, the universe doesn't begin with classical initial conditions, but emerges from a quantum state that exists outside of space and time. The wave function of the universe, proposed by Stephen Hawking and James Hartle, describes all possible cosmic histories simultaneously. In this view, asking what came before the Big Bang is like asking what lies north of the North Pole. Time itself emerges along with space during the quantum tunneling event that creates the universe. The apparent beginning of time in the Big Bang is not a moment when something started from nothing, but rather the boundary of space-time itself. The Hartle-Hawking no-boundary proposal suggests that the universe has no edge or boundary in time, but time nevertheless has a finite extent into the past. This is possible because time becomes space-like near the Big Bang, creating a geometry similar to the surface of a sphere. Just as the surface of the Earth has no edge, but still has finite area, the universe could have no temporal boundary, but still have finite age. Quantum cosmology makes specific predictions about the initial conditions of the universe that differ from classical Big Bang models. The theory suggests that the universe should emerge in its most probable quantum state, which turns out to be nearly flat and uniform. This could explain the apparent fine-tuning of initial conditions without requiring cosmic inflation or multiple universes. What if there was no singular beginning? What if the universe simply is, forever unfolding? In the deepest foundations of reality, where the familiar laws of physics begin to break down, quantum mechanics reveals a universe far stranger than our everyday experience suggests. At the smallest scales of space and time, particles exist in multiple states simultaneously. Reality becomes fundamentally probabilistic, and the very act of observation changes what we observe. These bizarre quantum effects, once thought to be limited to the microscopic world, may hold the key to understanding how our entire universe came into being. The quantum world operates according to rules that seem to defy common sense. A particle can be in two places at once, spinning clockwise and counterclockwise simultaneously, or existing and not existing until someone measures it. These superposition states collapse into definite realities only when observed or measured, suggesting that consciousness or measurement apparatus plays a fundamental role in determining what becomes real. Werner Heisenberg's uncertainty principle tells us that certain pairs of properties, like position and momentum, cannot be measured precisely at the same time. The more accurately we know where a particle is, the less we can know about how fast it's moving. This isn't just a limitation of our measuring instruments. It's a fundamental feature of nature itself. At quantum scales, the universe is inherently fuzzy and probabilistic rather than deterministic. Perhaps most remarkably, quantum mechanics shows us that empty space isn't really empty at all. The vacuum seethes with virtual particles that constantly pop into existence and disappear again, in tiny fractions of a second. These quantum fluctuations are not just theoretical constructs, they have real measurable effects. They create the Casimir force between closely spaced metal plates. They cause the slight shift in hydrogen spectral lines known as the Lamb shift, and they may have played a crucial role in the birth of our universe. The energy scale of these vacuum fluctuations depends on how small a region of space and time we examine. At the Planck scale, named after the physicist Max Planck, space and time themselves become uncertain. The Planck length is about 10 to the negative 35 meters, so small that a proton is larger than a Planck length by the same factor that a human is larger than a proton. At this scale, the smooth spacetime of Einstein's relativity gives way to a quantum foam of virtual black holes and wormholes appearing and disappearing in fleeting instants. When we apply quantum mechanics to cosmology, we discover that the universe itself might have emerged from these quantum fluctuations. In the 1970s, physicists like Edward Tryon and Alexander Vilenkin proposed that our entire universe could be understood as a quantum fluctuation of the vacuum, a cosmic accident that grew from nothing into everything we observe today. The basic idea seems almost absurd at first glance. How can something as vast as the universe, containing billions of galaxies and stretching across billions of light years, emerge from the quantum uncertainty of empty space? The answer lies in the peculiar nature of gravitational energy, and the possibility that the total energy of the universe might be exactly zero. In ordinary circumstances, creating matter requires energy, and energy conservation prevents us from making something from nothing. But gravity is different from other forces because it's always attractive. When you bring two masses together, they attract each other and release gravitational binding energy. This energy is considered negative because you have to add energy to the system to separate the masses again. If the universe contains just the right amount of matter, the positive energy of all the particles and radiation exactly cancels the negative gravitational binding energy of all the mass distributions. The total energy of such a universe would be zero, making it possible for the entire cosmos to emerge from a quantum fluctuation without violating energy conservation. This isn't just speculation. When cosmologists add up all the matter, radiation, and dark energy in our universe and compare it to the gravitational binding energy, they find that the total appears to be very close to zero. Our universe may indeed be the ultimate free lunch, a quantum accident that costs nothing to create and therefore doesn't violate any conservation laws. But how exactly would such a quantum creation event occur? The process involves a phenomenon called quantum tunneling, one of the most counterintuitive aspects of quantum mechanics. In the classical world, if you don't have enough energy to climb over a hill, you can't reach the other side. But in the quantum world, particles can tunnel through energy barriers even when they don't have enough energy to go over them. The mathematics of quantum mechanics shows that there's always some probability, however small, that a particle will appear on the other side of a barrier that should be impenetrable according to classical physics. This tunneling probability depends on the height and width of the barrier, becoming vanishingly small for large barriers, but never quite reaching zero. Alexander Vilenkin applied this concept to the creation of the universe itself. In his model, the initial state is a quantum vacuum with no space, no time, and no matter. This state can be thought of as sitting at the bottom of an energy valley. To create a universe, the system must tunnel through an energy barrier to reach a state where space and time begin to exist and expand. The probability of this tunneling event is extraordinarily small, but in the context of quantum cosmology, small probabilities can still lead to definite outcomes given enough opportunities. If the quantum vacuum exists timelessly, then even events with infinitesimally small probabilities will eventually occur. Our universe represents one such unlikely but inevitable quantum tunneling event. The tunneling process doesn't just create space and time, it also determines their initial property. The wave function that describes the tunneling process peaks at configurations corresponding to universes with specific characteristics. These quantum mechanical predictions for the initial state of the universe turn out to match remarkably well with the conditions needed to explain our observed cosmos. Quantum mechanics also provides a natural explanation for the tiny density variations that seeded the formation of galaxies and larger structures. During the earliest moments after quantum tunneling created our universe, space underwent rapid inflation that stretched microscopic quantum fluctuations to cosmic scales. These originally tiny variations in the quantum fields became the density perturbations we observe in the cosmic microwave background. The quantum origin of cosmic structure represents one of the most profound connections between the microscopic and macroscopic worlds. The galaxies we see today, including the Milky Way that contains our solar system, ultimately trace their origins to quantum uncertainty at the Planck scale. We are literally made of quantum fluctuations that have been amplified by cosmic inflation and shaped by billions of years of gravitational evolution. Stephen Hawking and James Hartle developed a more sophisticated approach to quantum cosmology based on path integrals, a mathematical technique that sums over all possible histories connecting initial and final states. In their no-boundary proposal, the universe has no initial conditions in the usual sense because time itself emerges from the quantum creation process. The Hartley-Hawking wave function describes the quantum state of the entire universe by summing over all possible four-dimensional geometries that have no boundary in time. This sounds abstract, but it has concrete consequences for the properties we should expect to observe. The calculation favors universes that are nearly flat, uniform, and dominated by inflation in their early phases, matching many features of our observed cosmos. In this quantum picture, asking what happened before the Big Bang becomes meaningless. Not because there was nothing before, but because the concept of before requires time, and time itself is created during the quantum tunneling event. It's similar to asking what lies north of the North Pole. The question contains a conceptual error, because north becomes undefined at that point. The many worlds interpretation of quantum mechanics, developed by Hugh Everett in the 1950s, suggests an even more radical possibility. If quantum superposition applies to the entire universe, then all possible outcomes of quantum measurements occur simultaneously in parallel realities. The wave function never collapses. Instead, it continuously branches into multiple versions of reality, corresponding to different measurement outcomes. Applied to cosmology, the many worlds interpretation suggests that the quantum tunneling process that created our universe actually created infinitely many universes simultaneously, each corresponding to a different possible outcome of the initial quantum fluctuation. Our universe is just one branch of an enormous quantum multiverse, where every possible cosmic history is equally real. In some branches, the tunneling process produces universes with slightly different physical constants or initial conditions. In others, the tunneling fails entirely and no universe emerges. We find ourselves in a branch where the tunneling succeeded and produced a universe capable of supporting complexity and life, but countless other branches contain universes with very different properties, or no universes at all. This quantum multiverse differs from the inflationary multiverse discussed in connection with eternal inflation. While the inflationary multiverse consists of different regions of a single quantum reality, the many worlds multiverse consists of genuinely separate quantum branches that can never communicate with each other. Both types of multiverse may exist simultaneously, creating a vast hierarchy of parallel realities. Quantum field theory, the marriage of quantum mechanics with special relativity, provides additional insights into cosmic origins. In quantum field theory, particles are excitations of underlying fields that fill all of space. Even in empty vacuum, these fields have zero-point energy due to quantum uncertainty. The total zero-point energy of all fields should contribute to the cosmological constant. But as we saw earlier, calculations give a result that's too large by an enormous factor. This vacuum energy problem represents one of the deepest puzzles in physics. Either our understanding of quantum field theory is seriously incomplete, or some unknown mechanism cancels most of the vacuum energy contributions. Some physicists speculate that the resolution might involve new physics at the Planck scale, where quantum gravity effects become important. Loop quantum gravity, one approach to quantum gravity, suggests that space and time have a discrete structure at the Planck scale, like a fabric woven from individual threads. In this picture, the smooth spacetime of general relativity emerges as an approximation valid only at scales much larger than the Planck length. The discrete structure provides a natural cutoff for quantum field theory calculations, potentially resolving the vacuum energy problem. String theory offers a different approach to quantum gravity by replacing point particles with tiny vibrating strings. The extra dimensions required by string theory provide new possibilities for how quantum fluctuations might manifest at cosmic scales. Some string theory models suggest that our entire universe might be a holographic projection of information encoded on a lower dimensional boundary, radically changing our understanding of space, time, and quantum mechanics. Causal set theory proposes that space-time is made of discrete events connected by causal relationships, like a cosmic network, where each node represents a quantum event, and connections represent the flow of information between events. In this approach, the familiar geometry of space and time emerges statistically from the underlying causal structure, much like thermodynamic properties emerge from the statistical behavior of large numbers of molecules. The role of consciousness in quantum mechanics has led some physicists to speculate about connections between quantum cosmology and the emergence of observers. If observation plays a fundamental role in quantum state reduction, then the existence of conscious observers might be necessary to actualize one particular cosmic history. from the infinite quantum superposition of possibilities. This observer effect in cosmology leads to profound questions about the relationship between mind and reality. Does consciousness create reality by observing it, or does reality create consciousness as a natural consequence of cosmic evolution? If quantum mechanics requires observers to collapse wave functions, how did the early universe evolve before any observers existed to measure it? Some interpretations suggest that the universe remains in quantum superposition until conscious observers evolve to measure it, at which point the entire cosmic history becomes retroactively determined. This backward causation might seem impossible, but quantum mechanics already demonstrates that future measurements can influence past states through phenomena like delayed choice experiments. The quantum Zeno effect shows that frequent measurements can freeze the evolution of quantum systems, while the reverse quantum Zeno effect shows that measurements can accelerate quantum transition. These effects suggest that observation isn't passive but actively participates in determining how quantum systems evolve. Applied to cosmology, conscious observation might play an active role in selecting which branch of the cosmic wave function becomes our experienced reality. Quantum information theory has revealed deep connections between information, computation, and the structure of space-time itself. Some physicists now believe that reality is fundamentally informational, with matter and energy emerging as patterns in an underlying computational substrate. If the universe is a quantum computer processing information about its own states, then cosmic evolution becomes a vast quantum calculation, whose output is the reality we observe. The holographic principle, derived from black hole physics, suggests that all the information in any region of space can be encoded on its boundary. This implies that our three-dimensional reality might be a holographic projection of information stored on a two-dimensional surface surrounding the observable universe. In this view, quantum mechanics isn't just important for understanding cosmic origins, it's the fundamental language in which reality itself is written. Perhaps the universe began not with a bang, but with a whisper from the quantum world. In the cosmic inventory of our universe, the familiar matter that makes up stars, planets, and our own bodies accounts for less than 5% of everything that exists. The remaining 95% consists of two mysterious components that we can detect only through their gravitational effects. These invisible substances, known as dark matter and dark energy, dominate the cosmos and may fundamentally reshape our understanding of how the universe began and evolved. Dark matter reveals itself through the way galaxies rotate and how light bends around massive galaxy clusters. When astronomers study spiral galaxies like our own Milky Way, they find that stars in the outer regions orbit the galactic center much faster than expected. According to Newton's laws of gravity, these outer stars should be moving slowly, just as the distant planets in our solar system orbit the Sun more leisurely than the inner planets. Instead, the rotation curves of galaxies remain remarkably flat, with stars at the edge moving at nearly the same speed as those closer to the center. This observation suggests that galaxies are embedded in massive halos of invisible matter that extends far beyond the visible stars. These dark matter halos provide the additional gravitational pull needed to keep the fast-moving outer stars bound to their galaxies. Computer simulations of cosmic structure formation can reproduce the observed distribution of galaxies only when they include about 5 times more dark matter than ordinary matter. In these simulations, dark matter forms a cosmic scaffolding that guides the formation of galaxies and galaxy clusters. Ordinary matter falls into the gravitational wells created by dark matter, eventually forming the stars and planets we can observe. The evidence for dark matter comes from multiple independent sources. Gravitational lensing observations show that massive galaxy clusters bend light from background galaxies in ways that require much more mass than can be seen in stars and gas. The cosmic microwave background radiation contains acoustic oscillations that depend on the ratio of dark matter to ordinary matter during the early universe. All of these observations point to the same conclusion, that most of the matter in the universe is invisible to our telescopes. Despite decades of searching, physicists have not been able to identify what dark matter actually is. The leading candidates are exotic particles that interact with ordinary matter only through gravity and possibly the weak nuclear force. These weakly interacting massive particles, or WIMPs, would have been produced in large quantities during the hot, early universe, and would have survived to the present day because they rarely interact with anything else. Underground detectors, shielded from cosmic rays, have searched for the rare occasions when dark matter particles might collide with atomic nuclei in laboratory experiments. Particle accelerators have attempted to create dark matter particles by smashing protons together at enormous energies. Space-based gamma-ray telescopes have looked for the radiation that should be produced when dark matter particles annihilate with each other in dense regions of space. So far, these searches have produced no convincing evidence for dark matter particles. Either the particles are even more elusive than expected, or dark matter consists of something completely different from what theorists have imagined. Some physicists have proposed alternative candidates, like axions, primordial black holes, or sterile neutrinos. Others have suggested that our understanding of gravity itself might be wrong, eliminating the need for dark matter entirely. Even more mysterious is dark energy, which appears to make up about 70% of the universe and causes the expansion of space to accelerate. This discovery came as a complete surprise in 1998, when two teams of astronomers studying distant supernovas found that the most remote galaxies were farther away than expected in a universe that was slowing down due to gravity. Type 1a supernovas serve as excellent standard candles because they always have roughly the same intrinsic brightness. By comparing how bright these supernovas appear with how bright they should be at their measured distances, astronomers can determine whether the expansion of the universe has been speeding up or slowing down over cosmic time. The supernova observations revealed that cosmic expansion began accelerating about 5 billion years ago, roughly when our solar system was forming. Before that time, the gravitational attraction of matter dominated cosmic evolution, gradually slowing the expansion that began with the Big Bang. But as the universe grew larger and matter became more diluted, the repulsive effect of dark energy began to dominate, causing the expansion to accelerate. The simplest explanation for dark energy is Einstein's cosmological constant, a term he originally added to his equations to prevent the universe from expanding or contracting. Einstein later called this his greatest blunder when Hubble's observations showed that the universe was indeed expanding. But the accelerating expansion discovered in 1998 suggests that Einstein's cosmological constant might be real after all. In this interpretation, empty space itself has energy that acts like a repulsive force on cosmic scales. This vacuum energy pushes space apart, overwhelming the attractive force of gravity when matter becomes sufficiently diluted. The energy density of this cosmic vacuum remains constant, even as space expands, providing a continuous source of repulsion that drives accelerating expansion. But when physicists try to calculate how much vacuum energy space should contain based on quantum field theory, they encounter a catastrophic failure. The theoretical prediction exceeds the observed value by a factor of 10 to the 120th power, making it the worst prediction in the history of physics. Something must be cancelling out most of the vacuum energy, but we have no idea what that mechanism might be. Alternative explanations for dark energy include new types of fields that change their properties over time. These quintessence models suggest that dark energy might not be constant, but could evolve as the universe ages. Some versions predict that dark energy will eventually weaken, allowing gravity to regain control, and potentially reversing cosmic expansion. Others suggest that dark energy might become stronger, leading to a Big Rip scenario, where accelerating expansion eventually tears apart all structures in the universe. The discovery of dark energy has profound implications for cosmic evolution and the ultimate fate of the universe. If dark energy remains constant or grows stronger over time, the universe will continue expanding and cooling forever. Galaxies will become increasingly isolated as space expands between them. Stars will eventually exhaust their nuclear fuel and die, leaving behind a cold, empty cosmos filled only with black holes and elementary particles. But dark energy might also hold clues to the nature of cosmic origins. Some theories suggest that dark energy is related to the same quantum fields that drove cosmic inflation in the early universe. If this connection is real, understanding dark energy might help us understand how the Big Bang itself occurred and why the universe has the properties we observe. The combined effects of dark matter and dark energy suggest that our universe is far stranger than early cosmologists imagined. Most of the cosmos consists of components that we cannot see directly and do not fully understand. These invisible substances control the formation of cosmic structures and determine the ultimate fate of everything we can observe. The existence of dark matter and dark energy also raises fundamental questions about the completeness of our physical theories. The Standard Model of particle physics, which successfully describes all known particles and forces except gravity, apparently misses 95% of the universe. Either we need to discover new particles and forces, or our basic understanding of space, time, and gravity requires revolutionary changes. Some physicists speculate that dark matter and dark energy might be manifestations of extra dimensions beyond the three spatial dimensions we experience directly. In these higher dimensional theories, gravity can leak into other dimensions, appearing as mysterious invisible matter and energy in our three-dimensional space. String theory and other approaches to quantum gravity predict the existence of such extra dimensions, though they remain undetected by current experiments. The search for dark matter and dark energy represents one of the greatest detective stories in modern science. We know these substances exist because of their gravitational effects, but their fundamental nature remains completely mysterious. Future space-based telescopes and underground detectors may finally reveal the identity of these cosmic enigmas, potentially revolutionizing our understanding of physics and cosmology. What we can't see may hold the answers we've been missing. One of the most profound questions in cosmology challenges our basic intuition about time itself. Must everything that exists have had a beginning? The Big Bang theory suggests that time started with the initial expansion, roughly 13.8 billion years ago. But some physicists now propose that the universe might be eternal, stretching infinitely into both the past and the future, without any ultimate origin or end. The concept of an eternal universe seems to contradict our everyday experience. Everything we observe in the world around us appears to have a beginning. People are born, buildings are constructed, and even mountains eventually erode away. The idea that something as vast and complex as the universe could have always existed challenges our deepest assumptions about causality and time. Yet modern physics has repeatedly shown us that the universe operates according to principles that defy common sense. Quantum mechanics reveals particles that exist in multiple states simultaneously. Relativity shows us that time runs at different rates depending on gravity and motion. At the most fundamental level, reality appears to be far stranger than our intuitions suggest. The notion of cosmic eternity has ancient roots. Hindu and Buddhist cosmologies described cycles of creation and destruction that repeat endlessly without beginning or end. The Greek philosopher Aristotle argued that the universe must be eternal because the idea of creation from nothing seemed logically impossible. Even some early Christian thinkers struggled with the concept of temporal creation, wondering what God was doing before creating the universe. But the scientific revolution seemed to settle the question in favor of a cosmic beginning. The discovery of cosmic expansion suggested that the universe was smaller and denser in the past. Extrapolating backward led inevitably to a moment of infinite density and temperature, the Big Bang singularity that marked the beginning of space and time. However, as we have seen, this singularity represents a breakdown of our physical theories rather than a description of actual events. When general relativity predicts infinite quantities, it signals that the theory has reached its limits and that new physics is needed. Quantum mechanics, which becomes important at extremely high densities, might eliminate the singularity and allow the universe to extend infinitely into the past. Loop quantum gravity provides one framework for understanding how this might work. In this approach, space and time have a discrete structure at the smallest scales, like a fabric woven from individual threads. This granular structure prevents matter from being compressed to infinite density, eliminating the singularities that plague classical general relativity. When loop quantum gravity is applied to cosmology, it suggests that our Big Bang was actually a big bounce from a previous contracting universe. As this earlier universe collapsed, it approached but never reached infinite density. Instead, quantum effects caused it to rebound when it reached the maximum possible density allowed by the discrete structure of spacetime. If this bouncing mechanism operates indefinitely, The universe could cycle through infinite expansions and contractions without ever having a first bounce or a final collapse. Each cycle would appear to have a beginning from the perspective of observers within that cycle, but the universe as a whole would be eternal. Our Big Bang would be just the most recent bounce in an infinite series stretching back forever. The cyclic model proposed by Paul Steinhardt and Neil Turok offers another vision of cosmic eternity. In their scenario, our three-dimensional universe exists on a membrane or brane floating in a higher dimensional space. This brane periodically collides with a parallel brane, creating the hot, dense conditions we associate with the Big Bang. These brane collisions occur on a regular schedule, perhaps every trillion years or so. Between collisions, the universe expands and cools, galaxies form and evolve, stars are born and die, and complex structures like planets and life emerge. But eventually, the expansion reverses, the branes approach each other again, and another collision resets the cosmic clock. In the ekpyrotic version of this model, the approaching branes don't actually touch, but come very close before bouncing apart again. The near collision creates a burst of radiation and particles that fills the universe with hot matter, effectively erasing all traces of the previous cycle. From the perspective of any observers who survived the transition, it appears that the universe began with this collision event. These cyclic models elegantly solve many of the fine-tuning problems that plague standard Big Bang cosmology. The flatness problem disappears, because the universe has infinite time to approach the critical density through natural evolution. The horizon problem is resolved, because distant regions had time to communicate during previous cycles. The models also predict specific signatures in the cosmic microwave background that future observations might be able to detect. String theory suggests yet another possibility for cosmic eternity through the concept of a pre-Big Bang phase. In some string cosmology models, our universe existed in a fundamentally different state before the hot Big Bang phase began. This pre-Big Bang universe might have been contracting rather than expanding, with very different physical properties than what we observe today. The transition between the pre-Big Bang and post-Big Bang phases occurs when the universe reaches a critical size or density, determined by the fundamental constants of string theory. This transition generates the hot radiation we associate with the Big Bang, but the underlying space-time geometry continues smoothly from the pre-Big Bang phase. Time extends infinitely into the past, eliminating the need for an ultimate beginning. In these models, the Big Bang becomes a phase transition rather than a moment of creation. It's similar to the way water transforms into steam when heated, a dramatic change in properties, but not the creation of something from nothing. The pre-Big Bang universe provides the raw material and initial conditions needed for the post-Big Bang evolution we observe. Eternal inflation presents perhaps the most radical vision of cosmic eternity. In this scenario, our observable universe is just one small bubble in an infinite multiverse that has been expanding forever. Different regions of this multiverse undergo inflation at different times and rates, creating a fractal-like structure of bubble universes within an eternally growing background. The multiverse as a whole has no beginning or end, but individual bubble universes like ours experience Big Bang-like events when inflation ends in their particular regions. These local Big Bangs occur continuously throughout the multiverse, creating new bubble universes with potentially different physical laws and constants. From this perspective, asking about the beginning of the universe is like asking about the beginning of a particular wave in an infinite ocean. Each wave has a definite start and end, but the ocean itself is eternal. Our Big Bang represents the formation of our particular cosmic bubble, but the multiverse that contains us has always existed. Quantum mechanics itself suggests ways that the universe might avoid having a definite beginning. In the many worlds interpretation, every possible quantum outcome occurs in parallel realities that branch continuously from a common source. If this branching has been happening forever, then the quantum multiverse extends infinitely into the past, even though individual branches might have definite starting points. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, has solutions that correspond to eternal quantum states. These solutions suggest that the universe might exist in a superposition of all possible histories, including histories that extend infinitely into the past. The apparent beginning we observe in our particular branch of reality might be an artifact of measurement rather than a fundamental feature of the cosmos. Some interpretations of quantum cosmology suggest that time itself might be emergent rather than fundamental. In these models, the basic structure of reality consists of timeless quantum information or abstract mathematical relationships. What we experience as time emerges from the correlations between different parts of this timeless quantum state. If time is emergent, then asking what came before the Big Bang becomes meaningless, in the same way that asking what lies north of the North Pole is meaningless. The question assumes the existence of time before time itself emerged, creating a logical contradiction. The universe doesn't have a beginning because beginning is a concept that only makes sense after time has emerged. The holographic principle, derived from black hole physics, suggests that all the information in any volume of space can be encoded on its boundary. Applied to cosmology, this principle implies that our three-dimensional universe might be a holographic projection of information stored on a two-dimensional surface at the edge of space. In holographic cosmology, the fundamental reality exists on this two-dimensional boundary, which might be timeless or have very different temporal properties than our three-dimensional experience. The Big Bang and cosmic evolution we observe could be emergent phenomena in the holographic projection rather than fundamental features of the underlying reality. Digital physics takes this idea even further by proposing that the universe is fundamentally computational. In this view, reality consists of information processing rather than matter and energy. What we perceive as particles and forces are patterns in an underlying computational substrate that might be eternal and timeless. If the universe is a computation, then its apparent beginning might simply represent the start of a particular program or algorithm. But the computational substrate that runs this program could be eternal, capable of running infinitely many different cosmic programs over infinite time. Our Big Bang would be just one execution of the cosmic program in an eternal computing system. The steady-state theory, though largely abandoned due to observational evidence, demonstrated that internally consistent cosmological models could be constructed without cosmic beginnings. While the original steady-state model failed to explain the cosmic microwave background and other observations, it showed that eternal universe models are mathematically viable. Modern variations of the steady-state idea, such as the quasi-steady-state cosmology proposed by Fred Hoyle and his collaborators, attempt to reconcile continuous creation with the observed properties of the universe. These models suggest that the cosmos undergoes periodic oscillations on very long timescales while maintaining overall steady-state properties. The question of cosmic eternity ultimately touches on some of the deepest philosophical issues in science. If the universe has no beginning, what does this mean for concepts of causation and explanation? Can we ever understand why the universe has the particular properties we observe if those properties are simply eternal features of reality? Some physicists argue that eternal universe models simply push the mystery back without solving it. Instead of asking why the universe began, we must ask why it has always existed, with just the right properties to support complexity and life. The fine-tuning problems that motivate many cosmological theories don't disappear in eternal models. They just take different forms. Others contend that eternity might actually provide better explanations than cosmic beginnings. If the universe has infinite time to explore all possibilities, then the particular combination of properties we observe becomes inevitable rather than mysterious. Given enough time, even extremely unlikely configurations will eventually occur and persist for finite periods. The anthropic principle becomes important in eternal universe scenarios. If the cosmos cycles through infinite configurations over infinite time, then observers will necessarily find themselves in periods when conditions are suitable for their existence. The apparent fine-tuning of cosmic properties might be a selection effect rather than evidence for design or multiple universes. What if there was no singular beginning? What if the universe simply is, forever unfolding? As we probe deeper into the mysteries of cosmic origins, we encounter not only the limits of our current theories, but also the fundamental boundaries of human knowledge itself. The universe may be far more complex and strange than our minds, evolved for survival on Earth, are capable of comprehending. Understanding these limitations might be just as important as pushing against them. Our brains evolved over millions of years, to help our ancestors survive in a very specific environment. We developed intuitions about medium-sized objects moving at everyday speeds, not about quantum particles existing in superposition or space-time curved by gravity. The mathematics that describes cosmic origins often defies visualization and challenges our deepest assumptions about reality. Consider how difficult it is to truly grasp the scale of the universe. We can recite that the observable cosmos stretches 93 billion light-years across, but what does this really mean? If Earth was shrunk to the size of a grain of sand, the nearest star would still be over 4 kilometers away. The Milky Way galaxy would span the entire distance from Earth to the Sun, and this represents just our local cosmic neighborhood. When we try to imagine the Big Bang, we inevitably fall back on familiar analogies that may mislead more than they illuminate. We picture an explosion expanding into empty space, but the Big Bang was actually the expansion of space itself. We imagine a moment of creation, but time itself emerged during this process. Our language evolved for describing everyday experiences lacks adequate concepts for these cosmic phenomena. The challenge goes beyond mere scale or unfamiliarity. Some aspects of quantum mechanics and cosmology may be fundamentally incomprehensible to minds like ours. When physicists say that a particle exists in multiple states simultaneously until observed, they aren't describing something that can be visualized or understood intuitively. The mathematics works and makes testable predictions, but the underlying reality remains mysterious. The measurement problem in quantum mechanics illustrates these limitations. We can calculate the probability that a particle will be found in different locations, but we cannot explain why measurement causes the wave function to collapse into a single definite state. After nearly a century of quantum mechanics, physicists still debate what actually happens during measurement and whether consciousness plays a role. Similarly, we can detect dark matter through its gravitational effects and map its distribution throughout the universe, but we have no idea what it actually is. Our most sophisticated theories predict particles that have never been observed. Our deepest underground detectors and most powerful accelerators have found no convincing evidence for the exotic matter that supposedly makes up most of the cosmos. The problem isn't just technological. Even if we could build perfect detectors and unlimited energy accelerators, we might still face fundamental barriers to understanding. Some aspects of reality might be inherently unknowable, not because of practical limitations, but because of the nature of knowledge itself. Gödel's incompleteness theorems show that even in mathematics, the most rigorous form of human reasoning, there are truths that cannot be proven within any consistent logical system. If mathematics itself has fundamental limits, how much more so might our understanding of physical reality? Perhaps the deepest questions about cosmic origins will always remain beyond our reach. The cosmic horizon provides another example of fundamental limits. We can only observe the universe within a sphere, centered on Earth, and bounded by the distance light has traveled since the Big Bang began. Beyond this horizon lies the unobservable universe, which might be infinite in extent and could have very different properties than what we see. Even within the observable universe, we face practical limits on how far back in time we can peer. The cosmic microwave background radiation represents the earliest epoch we can observe directly, when the universe became transparent to light, roughly 380,000 years after the Big Bang. Everything that happened before this time remains hidden behind a wall of hot plasma. Gravitational wave detectors might eventually allow us to probe even earlier epochs, perhaps back to the first fraction of a second after the Big Bang began. But quantum effects near the Planck time, about 10 to the negative 44 seconds, might create an absolute barrier to observation. At these scales, the very concepts of space and time break down, making the notion of observation meaningless. The multiverse concept, while scientifically motivated, raises profound questions about the limits of empirical knowledge. If we live in one bubble universe among infinitely many, most with different physical laws, how can we ever test theories about the multiverse as a whole? We might develop mathematical frameworks that predict multiverse properties, but we could never observe other universes directly. Some philosophers of science argue that multiverse theories are not really scientific because they make no testable predictions about our observable reality. If any possible observation can be explained by appeal to different properties in other universe bubbles, then the theory explains everything and therefore explains nothing. the multiverse might be beyond the reach of scientific method itself. String theory faces similar challenges. Despite decades of development by brilliant physicists, string theory has made few testable predictions about observable phenomena. The theory requires extra dimensions that are compactified to invisibly small sizes and predicts an enormous landscape of possible vacuum states. Critics argue that string theory has become mathematics rather than physics. The anthropic principle adds another layer of complexity to these epistemological problems. If we can only observe universe properties that are compatible with our existence, then many apparent cosmic coincidences might be selection effects rather than deep truths requiring explanation. But this reasoning can quickly become circular, explaining away all observations as inevitable consequences of our existence. Human psychology itself introduces biases that may limit our understanding. We have a strong tendency to seek patterns and explanations even when none exist. We prefer simple, elegant theories, even when reality might be irreducibly complex. We project familiar concepts onto unfamiliar phenomena, potentially missing entirely different ways of organizing reality. The history of science shows how often human intuitions have led us astray. Common sense told us that the Earth was flat and stationary, that heavier objects fall faster than lighter ones, and that space and time were absolute and unchanging. Each scientific revolution required abandoning cherished beliefs and embracing counterintuitive ideas. Perhaps the greatest revolution still awaits, one that will require abandoning our assumption that reality can be understood by minds like ours. The universe might operate according to principles so alien to human cognition that we can never truly comprehend them, only develop mathematical tools that allow limited prediction and control. Language itself may impose fundamental limits on cosmic understanding. The words we use to describe reality carry implicit assumptions about how the world works. When we speak of particles and waves, cause and effect, beginning and end, we import conceptual frameworks that might be fundamentally inadequate for describing cosmic origins. Some physicists have suggested that future progress might require developing entirely new languages, perhaps based on mathematical structures that have no analog in everyday experience. These languages might allow us to manipulate concepts that cannot be translated into ordinary words, much as advanced mathematics allows calculations that cannot be performed with simple arithmetic. The collective nature of scientific knowledge provides some hope for transcending individual limitations. No single human mind could understand all of modern physics, but the scientific community as a whole has developed frameworks that surpass any individual understanding. Perhaps this collective intelligence can continue pushing beyond apparent barriers. Computer simulations offer another way to extend human cognitive abilities. We can create virtual universes that evolve according to the laws of physics and observe their behavior over cosmic timescales. These simulations might reveal patterns and connections that would be impossible to detect through mathematical analysis alone. Artificial intelligence might eventually surpass human cognitive abilities and discover principles of cosmic origins that remain forever beyond human comprehension. But this raises the question of whether such discoveries would constitute human understanding or merely the creation of tools whose operations we cannot fathom. The question of consciousness itself remains one of the deepest mysteries in science. We don't understand how subjective experience arises from objective physical processes. If consciousness plays a fundamental role in quantum measurement, as some interpretations suggest, then understanding cosmic origins might require solving the mystery of consciousness itself. Perhaps the search for ultimate cosmic understanding is itself an illusion, a projection of human desires onto an indifferent universe. Maybe reality simply is, without deeper meaning or purpose that minds like ours could discover. The universe might be under no obligation to be comprehensible to any particular type of observer. Yet the history of science also demonstrates the remarkable power of human reason to uncover hidden truths about reality. From Newton's laws to quantum mechanics to general relativity, we have repeatedly discovered that the universe operates according to mathematical principles that can be expressed in precise, testable theories. Each breakthrough seemed impossible before it occurred. The limits we face today might be temporary rather than fundamental. New mathematical tools, experimental techniques, or conceptual frameworks might eventually overcome barriers that seem insurmountable now. What appears to be the end of human understanding might be merely the beginning of a new phase of discovery. We may never fully understand the universe's origins, but it is in asking these questions that we come closer. The quest to understand cosmic origins continues to evolve as new technologies and theoretical frameworks push the boundaries of what we can observe and comprehend. In the coming decades, revolutionary instruments and innovative approaches may finally resolve some of the deepest mysteries about how our universe began, or they may reveal that reality is even stranger than we currently imagine. The James Webb Space Telescope, launched in 2021, has already begun transforming our view of the early universe. This remarkable instrument can peer deeper into space and further back in time than any previous telescope, observing galaxies that formed when the cosmos was only a few 100 million years old. These ancient galaxies appear larger and more mature than theoretical models predicted, suggesting that our understanding of early cosmic evolution may need significant revision. Future space telescopes will push even further into the cosmic past. The proposed Cosmic Origins Spectrometer could detect the very first stars that ever formed, massive giants that lived fast and died young, enriching the universe with heavy elements for the first time. The Advanced Technology Large Aperture Space Telescope might observe galaxies forming when the universe was only 50 million years old, revealing how the first cosmic structures emerged from the primordial darkness. Ground-based observatories are also becoming more powerful. The Extremely Large Telescope, with a mirror 40 meters across, will collect 13 times more light than any existing telescope. When combined with adaptive optics that correct for atmospheric turbulence, these instruments will achieve unprecedented clarity in observing distant galaxies and measuring their properties. But perhaps the most exciting frontier involves gravitational wave astronomy. The Laser Interferometer Gravitational Wave Observatory and its European counterpart Virgo have already detected dozens of collisions between black holes and neutron stars. These observations provide a completely new way to study the universe, one that doesn't depend on electromagnetic radiation at all. Future gravitational wave detectors will be far more sensitive than current instruments. The proposed Cosmic Explorer will have arms 40 kilometers long, 10 times larger than current detectors. The European Einstein Telescope will be built underground to minimize vibrations, using cryogenic cooling to reduce thermal noise. These advanced detectors might be sensitive enough to observe gravitational waves from the Big Bang itself. If cosmic inflation really occurred in the early universe, it should have produced a background of primordial gravitational waves that still permeates space today. Detecting these ancient ripples would provide direct evidence for inflation and reveal details about physics at energies far beyond what any particle accelerator could achieve. The discovery would represent one of the greatest triumphs in the history of cosmology. Space-based gravitational wave detectors will open even more possibilities. The Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will consist of 3 spacecraft flying in formation millions of kilometers apart. This configuration will be sensitive to gravitational waves from massive black hole mergers throughout cosmic history, providing a census of how these exotic objects formed and evolved. The study of cosmic microwave background radiation continues to yield new insights about the early universe. The Planck satellite, which completed its mission in 2013, mapped temperature variations across the sky with exquisite precision. Future missions, like the proposed CMB Stage 4 experiment, will focus on measuring the polarization of this ancient light, which carries information about gravitational waves and other primordial phenomena. Polarization measurements are technically challenging, but scientifically crucial. The pattern of polarization in the cosmic microwave background can reveal whether cosmic inflation occurred and provide details about the physics that drove it. These observations might also detect signatures of cosmic strings, topological defects that could have formed during phase transitions in the early universe. Neutrino astronomy represents another emerging frontier. These ghostly particles interact so weakly with matter that they can travel from the most distant regions of the universe virtually unimpeded. The IceCube Neutrino Observatory, built into the Antarctic ice sheet, has already detected high-energy neutrinos from distant galaxies. Future neutrino telescopes might be sensitive enough to observe the cosmic neutrino background. a relic from when the universe was only 1 second old. Particle physics experiments continue to search for the exotic matter that theoretical models predict should exist. Underground detectors are becoming increasingly sensitive in their hunt for dark matter particles. Next-generation experiments will probe interaction cross-sections many orders of magnitude smaller than current limits, potentially finally detecting the particles that make up most of the matter in the universe. The Large Hadron Collider at CERN continues to explore higher energy scales, searching for new particles and forces that might explain cosmic mysteries. Plans for even more powerful accelerators, such as the proposed Future Circular Collider with a circumference of 100 kilometers, could probe energies approaching those present during cosmic inflation. Theoretical physics is also advancing rapidly. String theory continues to develop new mathematical tools and make connections with observable phenomena. Loop quantum gravity is making testable predictions about the cosmic microwave background and gravitational wave signatures. Other approaches to quantum gravity, such as causal dynamical triangulation and asymptotic safety, are also maturing and offering new perspectives on cosmic origins. Computer simulations are becoming increasingly sophisticated as computational power continues to grow. The largest cosmological simulations now model the evolution of trillions of particles over billions of years, reproducing the observed large-scale structure of the universe in remarkable detail. Future simulations will include even more realistic physics, modeling the formation of the first stars and galaxies with unprecedented accuracy. Artificial intelligence is beginning to play an important role in cosmological research. Machine learning algorithms can identify patterns in vast astronomical datasets that would be impossible for humans to detect. These tools are already being used to classify galaxies, detect gravitational wave signals, and analyze cosmic microwave background data. Future AI systems might discover entirely new types of cosmic phenomena or reveal hidden connections between seemingly unrelated observations. The combination of quantum computing and cosmological simulation offers intriguing possibilities. Quantum computers are naturally suited to simulating quantum systems, potentially allowing detailed modeling of the quantum processes that might have occurred during cosmic inflation or the Big Bang itself. These simulations could reveal whether proposed mechanisms for cosmic origins are actually viable. New mathematical techniques are also opening fresh approaches to old problems. The holographic principle, originally developed to understand black hole physics, is being applied to cosmology with surprising results. The AD-CFT correspondence, which relates theories of gravity to quantum field theories, might provide new tools for understanding the quantum nature of space-time itself. Information theory is revealing deep connections between computation, thermodynamics, and cosmology. Some physicists now propose that the universe itself might be understood as an information processing system, with physical laws emerging from computational principles. This perspective could fundamentally change how we think about cosmic origins and evolution. The search for life beyond Earth also informs our understanding of cosmic history. The discovery of thousands of exoplanets has shown that planetary systems are common throughout the galaxy. Future telescopes will be able to analyze the atmospheres of these distant worlds, potentially detecting biosignatures that would indicate the presence of life. If life is common in the universe, it might provide clues about cosmic evolution and the conditions necessary for complexity to emerge. If life is rare, it might tell us something about the fine-tuning of physical constants or the frequency of suitable cosmic conditions. Either result would inform our understanding of why the universe has the properties we observe. The coming decades may witness the resolution of some of cosmology's greatest mysteries. We might finally understand the nature of dark matter and dark energy, detect primordial gravitational waves, or discover signatures of the multiverse. Alternatively, we might find that the universe is even more mysterious than we currently suspect, with new puzzles replacing the ones we solve. The story of cosmic origins remains unfinished, waiting for the next chapter to be written by observations yet to be made and theories yet to be developed. Each new discovery brings us closer to understanding our place in the vast cosmic story. Even as it reveals new depths of mystery and wonder, the universe's story is still unfolding. Our understanding, too, is still in progress. The search for cosmic origins extends far beyond the realm of physics and astronomy into the deepest questions of human existence. What does it mean for the universe to have a beginning? How should we understand our place in a cosmos that might be eternal, cyclic, or one of infinitely many? These questions touch the very core of how we make sense of life, meaning, and our connection to the vast universe around us. Throughout human history, creation stories have served not merely to explain how the world came to be, but to provide frameworks for understanding purpose, morality, and meaning. The scientific revolution promised to replace these ancient narratives with objective, evidence-based accounts of cosmic origins. Yet, as our scientific understanding has deepened, it has raised as many philosophical questions as it has answered. If the Big Bang Theory is correct, and the universe truly began 13.8 billion years ago, what does this tell us about the nature of existence itself? Does a cosmic beginning imply a cosmic purpose, or can meaning emerge from purely natural processes? The idea that everything we know emerged from a quantum fluctuation or a random collision of higher dimensional brains seems to drain significance from human life and consciousness. Yet this perspective might be fundamentally mistaken. The fact that complex structures like galaxies, stars, planets, and living beings can emerge from simple initial conditions might actually be more remarkable than any designed creation. The laws of physics appear to be precisely tuned to allow the universe to develop from a hot, dense state into the rich, structured cosmos we observe today. This apparent fine-tuning raises profound questions about why the universe has the particular properties it does. Some interpret cosmic fine-tuning as evidence for intelligent design or cosmic purpose. The fundamental constants of physics seem to fall within narrow ranges that allow for the formation of atoms, stars, and planets. If the strong nuclear force were slightly weaker, atoms heavier than hydrogen could not exist. If it were slightly stronger, hydrogen would be unstable and the universe would contain only heavy elements. Similar fine-tuning arguments apply to dozens of other physical parameters. Others argue that fine-tuning is an illusion created by our limited perspective. In an infinite multiverse containing all possible combinations of physical laws, some universes will inevitably have properties compatible with the existence of observers. We find ourselves in such a universe not because it was designed for us, but because we could not exist anywhere else. The anthropic principle transforms apparent cosmic purpose into a simple selection effect. But the multiverse solution to fine-tuning raises its own philosophical challenges. If all possible universes exist somewhere in an infinite multiverse, then everything that can happen does happen. Every possible version of your life is being lived by countless copies of yourself in parallel realities. This notion of infinite duplication seems to undermine the uniqueness and significance of individual existence. The concept of cosmic eternity presents different but equally profound challenges to human meaning-making. If the universe has always existed and always will exist, cycling through infinite expansions and contractions, or continuously creating new bubble universes, then our entire cosmic epoch becomes an infinitesimal moment in an endless story. From this eternal perspective, nothing we do can have lasting significance. Yet eternity might also be liberating rather than depressing. If the universe has infinite time to explore all possibilities, then every moment of beauty, love, and understanding becomes an eternal part of cosmic history. The experiences that give meaning to human life are not diminished by being temporary. They are made precious by their rarity and fragility in the vast sweep of cosmic time. The quantum nature of reality adds another layer of philosophical complexity. If consciousness plays a fundamental role in quantum measurement, as some interpretations suggest, then observers might be active participants in creating reality rather than passive witnesses to an objective universe. This participatory universe challenges the clear distinction between subject and object that underlies much of modern science and philosophy. The many worlds interpretation pushes this participatory element even further. In the quantum multiverse, every possible outcome of every quantum measurement occurs in parallel realities. Your consciousness navigates through this infinite branching structure, experiencing one particular path while countless copies experience all the alternatives. This view makes every choice and every moment simultaneously inevitable and infinitely significant. The possibility that time itself might be emergent rather than fundamental challenges our most basic assumptions about causation and meaning. If time emerges from timeless quantum information or mathematical relationships, then questions about cosmic beginnings become category errors. The universe doesn't have a beginning because beginning presupposes time, and time is a derived rather than fundamental aspect of reality. This timeless perspective might resolve some philosophical puzzles while creating others. If the deepest level of reality is timeless, then perhaps human meanings and values are also timeless, existing as eternal mathematical truths rather than temporary biological accidents. Love, beauty, and understanding might be fundamental features of reality rather than emergent properties of complex brains. The search for cosmic origins also raises questions about the relationship between science and other ways of knowing. Religious and spiritual traditions have developed sophisticated frameworks for understanding cosmic meaning that don't depend on detailed knowledge of physics and astronomy. These traditions often emphasize direct experience, contemplative practice, and wisdom traditions that claim to reveal truths about the nature of reality that are inaccessible to scientific method. Some physicists have noted striking parallels between modern cosmology and ancient mystical traditions. The quantum universe of superposition and entanglement resembles the interconnected cosmos described in Hindu and Buddhist philosophy. The timeless, dimensionless realm that might underlie space-time echoes the eternal, formless ground of being described by mystics across cultures. These parallels might be mere coincidence, or they might point to deep truths about reality that can be approached through multiple paths. The question of consciousness remains central to any philosophical interpretation of cosmic origins. We don't understand how subjective experience arises from objective physical processes. The hard problem of consciousness, the question of why there is something it is like to be a conscious being, remains unsolved, despite advances in neuroscience and cognitive psychology. If consciousness is fundamental rather than emergent, as some philosophers and physicists propose, then it might play a role in cosmic evolution that we are only beginning to understand. Conscious observers might be necessary to actualize particular branches of the cosmic wave function, making consciousness a cosmic force rather than a biological accident. The possibility that advanced civilizations elsewhere in the universe have already grappled with these questions adds another dimension to cosmic philosophy. If intelligence is common in the cosmos, then our struggles to understand cosmic origins might be just one chapter in a vast ongoing conversation among conscious beings throughout the universe. Our scientific discoveries and philosophical insights become part of a cosmic community of minds, seeking to understand their place in existence. The scale of cosmic time also challenges human meaning-making. If the universe lasts for trillions of years, then human civilization represents less than a billionth of cosmic history. Our entire species, with all its achievements and struggles, occupies an infinitesimal moment in the cosmic timeline. This temporal insignificance can seem overwhelming, but it might also highlight the preciousness of consciousness and meaning in a vast, mostly Perhaps the most profound implication of cosmic origins research is that the universe appears to be comprehensible to minds like ours. Despite the enormous scales of space and time involved, despite the quantum weirdness and relativistic effects that govern cosmic evolution, human beings have been able to construct mathematical theories that explain and predict cosmic phenomena with remarkable accuracy. This comprehensibility is not obviously necessary. The universe could have been chaotic, random, or governed by principles completely beyond human understanding. Instead, we find that the cosmos operates according to elegant mathematical laws that finite minds can discover and appreciate. This suggests a deep connection between consciousness and cosmic structure that we are only beginning to explore. The aesthetic dimension of cosmic origins research also deserves attention. The mathematical equations that describe the birth and evolution of the universe are often described as beautiful by the physicists who work with them. The patterns and symmetries that govern cosmic structure appeal to the same sense of beauty that draws us to art, music, and poetry. This aesthetic dimension suggests that beauty might be a fundamental feature of reality, rather than a subjective human projection. The ultimate questions about cosmic origins may never receive final answers, but the search itself transforms our understanding of what it means to be human in a vast, ancient, and mysterious cosmos. Each new discovery about the universe's beginning or potential eternity changes how we see ourselves and our place in the larger story of existence. Whether the universe began with a Big Bang or has always existed, whether it is unique or one of infinitely many, whether consciousness plays a fundamental role or emerges from complexity, the search for cosmic origins continues to reveal new depths of mystery and wonder. These discoveries invite us to expand our sense of what is possible and to find meaning, not in final answers, but in the ongoing quest for understanding. The search for the universe's beginning may be a search for meaning itself. As we reach the end of our journey through the mysteries of cosmic origins, we find ourselves not with final answers, but with deeper questions and expanded wonder. The Big Bang Theory, which began as a simple observation about receding galaxies, has grown into a comprehensive framework for understanding cosmic evolution. Yet each answer it provides seems to unveil new mysteries waiting to be explored. We have seen how Edwin Hubble's discovery of cosmic expansion led to the radical idea that the universe itself had a beginning. We have followed the development of this concept through the detection of cosmic microwave background radiation, the precise measurements of light element abundances, and the detailed mapping of large-scale cosmic structure. The evidence for the Big Bang Theory is compelling and has transformed our understanding of space, time, and our place in the cosmos. But we have also examined the growing list of problems that challenge this elegant theory. The Horizon Problem asks how distant regions of space could have reached thermal equilibrium without ever being in causal contact. The Flatness Problem questions why the universe seems so precisely balanced on the knife edge between expansion and collapse. The Missing Matter and Energy Problems force us to acknowledge that 95% of the universe consists of mysterious components we cannot directly observe. These challenges have inspired physicists to propose remarkable alternatives to the traditional Big Bang picture. The steady-state theory, though ultimately contradicted by observations, demonstrated that eternal universes could be scientifically viable. Cyclic cosmology suggests that our Big Bang might have been just the latest bounce in an infinite series of expansions and contractions. Loop quantum gravity proposes that quantum effects prevent the formation of singularities, allowing cosmic evolution to extend infinitely into the past. String theory opens the possibility of higher dimensional realities where our universe exists on a brane floating in spaces we cannot directly perceive. Eternal inflation envisions a multiverse where Big Bang events occur continuously, creating infinite bubble universes with different physical laws. Each of these alternatives challenges our basic assumptions about time, space, and cosmic uniqueness. The quantum nature of reality adds yet another layer of mystery to cosmic origins. At the deepest level, the universe appears to be fundamentally probabilistic rather than deterministic. Virtual particles constantly appear and disappear in the quantum vacuum, and our entire cosmos might have emerged from just such a quantum fluctuation. The wave function of the universe might describe all possible cosmic histories simultaneously, with observations somehow selecting the particular reality we experience. Dark matter and dark energy, the invisible components that dominate our universe, remind us how much we still don't know about the fundamental nature of reality. These substances affect the formation of cosmic structures and determine the ultimate fate of the universe. Yet their identities remain completely mysterious despite decades of intensive searching. They represent perhaps the greatest puzzles in modern cosmology. The possibility that the universe might have no beginning at all challenges our deepest intuitions about causation and existence. If time itself is emergent rather than fundamental, then questions about what came before the Big Bang become meaningless. If the universe has always existed in some form, cycling through infinite transformations, or existing timelessly at the deepest level, then our entire conception of cosmic origins requires radical revision. Throughout our exploration, we have encountered the fundamental limits of human understanding. Our minds evolved to comprehend medium-sized objects moving at everyday speeds, not quantum superpositions or curved spacetime. The mathematics that describes cosmic origins often defies visualization and challenges our most basic concepts about reality. We may be approaching questions that are simply too profound for minds like ours to fully grasp. Yet the future of cosmology holds remarkable promise. New telescopes are already revealing surprises about the early universe, showing galaxies that formed earlier and grew faster than our theories predicted. Gravitational wave detectors might soon observe ripples in space-time itself that originated during the first moments after the Big Bang. Advanced particle physics experiments continue searching for the exotic matter that theory suggests should exist. Artificial intelligence and quantum computing may provide tools for exploring cosmic questions that exceed the limits of human cognition. Computer simulations of increasing sophistication allow us to model the evolution of entire universes and test our theories against observation. The combination of new technologies and innovative theoretical approaches may finally resolve some of cosmology's deepest mysteries. The philosophical implications of cosmic origins research extend far beyond physics and astronomy. Questions about cosmic beginnings touch the very core of human meaning-making. Whether the universe had a definite beginning or has always existed, whether we live in a unique cosmos or one of infinitely many, these discoveries change how we understand our place in the larger story of existence. The apparent fine-tuning of physical constants raises profound questions about purpose and design in cosmic evolution. The quantum measurement problem suggests that consciousness might play a fundamental role in determining what becomes real. The comprehensibility of the universe to human minds hints at deep connections between cosmic structure and the nature of consciousness itself. Perhaps most remarkably, the universe appears to be not only comprehensible, but beautiful. The mathematical equations that describe cosmic evolution possess an elegance and symmetry that appeals to our aesthetic sense. The patterns and structures that emerge from simple initial conditions display a complexity and richness that inspire wonder and reverence. This aesthetic dimension suggests that beauty might be a fundamental feature of reality, rather than a mere human projection. As we stand at the threshold of new discoveries, we carry with us both the achievements and the humility that come from decades of cosmic exploration. We have learned that the universe is far stranger and more wonderful than our ancestors could have imagined. We have also learned that each answer leads to new questions. Each solution reveals new mysteries, and each level of understanding opens doors to even deeper levels of complexity. The Big Bang Theory may not be the final answer to cosmic origins. It may be modified beyond recognition by future discoveries, or it may be replaced entirely by radically different frameworks that we cannot yet imagine. But regardless of how our theories evolve, the sense of wonder that drives cosmological research will continue to inspire new generations of scientists and thinkers. The quest to understand cosmic origins represents one of humanity's greatest intellectual adventures. It connects us to the deepest questions about existence, consciousness, and meaning. It reminds us that we are part of something vastly larger than ourselves, participants in a cosmic story that has been unfolding for billions of years and will continue long after our individual lives have ended. In seeking to understand where the universe came from, we learn something profound about where we came from. In contemplating cosmic evolution, we gain perspective on human evolution. In marveling at the emergence of complexity from simplicity, we appreciate the remarkable fact of our own existence as conscious beings, capable of wondering about our origins. The story of cosmic origins remains unfinished, its next chapters waiting to be written by observations yet to be made and insights yet to be discovered. Each new piece of evidence, each theoretical breakthrough, each moment of understanding adds to humanity's ongoing conversation with the cosmos. We are not merely observers of this grand story, we are participants in it, conscious beings through whom the universe comes to know itself. Whether the Big Bang Theory survives future scrutiny or gives way to something entirely unexpected, the search for cosmic truth continues. In this search, we find not only knowledge about the universe, but wisdom about ourselves. The greatest discovery may not be a final theory of cosmic origins, but the realization that the capacity for wonder, curiosity, and understanding is itself one of the most remarkable features of our mysterious cosmos. The Big Bang Theory may not be the final answer, but in its imperfections, it invites us to look deeper, to wonder more. Perhaps the greatest discovery lies not in knowing, but in the questions we continue to ask.